Imagine standing on the edge of an ancient Roman road, perfectly straight, stretching beyond the horizon. 2,000 years ago, these roads connected an empire, allowing goods, armies, and ideas to flow across vast distances with unprecedented efficiency. Now imagine a similar system, not connecting cities or countries, but connecting stars. This is the concept of an interstellar highway system, an idea that could fundamentally transform how intelligent civilizations navigate the cosmos. When we talk about an interstellar highway system, we are not referring to literal roads paved through the vacuum of space. Instead, we are discussing a network of established routes, infrastructure, and technologies that would make travel between star systems as routine and predictable as traveling between major cities on Earth. Think of it as the difference between an explorer hacking through uncharted jungle with a machete versus a traveler driving on a well-maintained interstate highway. Both reach their destination, but the experience, efficiency, and reliability are worlds apart. The concept encompasses several interconnected ideas. First, there would be optimal travel routes between stars, corridors through space that minimize travel time and energy expenditure. Second, there would be way stations or infrastructure positioned along these routes, providing resources, repairs, or gravitational assists. Third, there would be standardized navigation systems, allowing any vessel to safely traverse these cosmic corridors. And fourth, there would be communication networks enabling real-time or near real-time coordination across these vast distances. To understand why this concept matters, we need to grasp the fundamental challenges of interstellar travel. The distances involved are almost incomprehensibly large. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That means that even traveling at the speed of light, which is impossible for any object with mass, according to our current understanding of physics, it would take more than 4 years to reach this nearest stellar neighbor. With current chemical rocket technology, the same journey would take tens of thousands of years. These distances create profound problems. A spacecraft traveling between stars cannot simply point itself at a destination and fly in a straight line. It must account for the motion of both its starting point and its destination, as stars are not stationary but orbit around the galactic center. It must carry or generate enough energy to sustain its journey. It must protect its crew or cargo from radiation, micrometeorites, and the psychological challenges of extended isolation. And it must do all this with limited ability to receive help if something goes wrong. Current space travel concepts treat each mission as essentially unique. When we send a probe to Mars or beyond, we calculate a specific trajectory, build a spacecraft for that particular mission, and hope everything goes according to plan. There is no infrastructure waiting at the destination, no established route that others have traveled before, no system of support stations along the way. Every mission is, in essence, a venture into the unknown. An interstellar highway system would change this paradigm entirely. Instead of each mission being a unique endeavor, travel between certain stars would become standardized, predictable, and supported by infrastructure. This is analogous to how the development of road systems transformed human civilization. Before road networks existed, traveling between settlements was dangerous, slow, and unpredictable. Travelers had to navigate difficult terrain, defend themselves against threats, and carry everything they needed for the journey. The construction of roads changed everything. Suddenly, travel times became predictable. Trade flourished because merchants could reliably transport goods. Military forces could be rapidly deployed. Information could spread more quickly. Economic and cultural integration accelerated dramatically. The impact of roads on human civilization cannot be overstated. The Roman road system, for instance, stretched over 250,000 miles at its peak, connecting regions from Britain to North Africa, from Spain to the Middle East. These roads lasted for centuries, many still in use today. They enabled the rise of one of history's greatest empires, not through superior military might alone, but through superior logistics and connectivity. Similarly, in more recent history, the United States interstate highway system, begun in the 1950s, transformed American society. It enabled efficient cross-country transport of goods, facilitated suburban expansion, accelerated economic growth, and fundamentally altered how Americans lived and worked. The economic return on the investment in this highway system has been estimated at $6 for every dollar spent. Now transpose this concept to interstellar space. Imagine if traveling from Earth to a colony orbiting Alpha Centauri was as routine as flying from New York to London. Imagine if freight vessels regularly carried resources between star systems along established routes. Imagine if emergency rescue ships could be dispatched from waypoints along these routes if a vessel encountered trouble. Imagine if pioneers could establish new colonies, knowing that they would remain connected to their home civilization, not isolated for generations. Why would humanity, or any advanced civilization, need such a system? The answer lies in the fundamental nature of expansion and survival. First, there is the practical matter of resources. While space contains virtually unlimited resources, they are not evenly distributed. Some star systems might be rich in heavy elements, others in ice and water, others in ideal habitable planets. An interstellar highway system would enable efficient transport of resources from where they are abundant to where they are needed, just as terrestrial trade routes allowed ancient civilizations to obtain goods unavailable in their local regions. Second, there is the question of redundancy and survival. One of the often cited reasons for becoming a multiplanetary species is that it protects against existential risks. If humanity remains confined to Earth, a single catastrophic event such as an asteroid impact, supervolcanic eruption, or nuclear war could potentially end our species. Spreading across multiple star systems provides even greater insurance. However, these colonies would need to remain connected to share knowledge, technology, and support. An isolated colony could fail due to unforeseen challenges. A connected network of colonies could support each other through difficult periods. Third, there is the acceleration of knowledge and cultural exchange. Human progress has always been fastest when different groups could readily exchange ideas. The Silk Road was not just a trade route for goods, but a conduit for knowledge, religious ideas, technological innovations, and cultural practices. An interstellar highway system would enable different branches of civilization to learn from each other's experiences, avoiding pitfalls and sharing breakthroughs. Fourth, there is the simple human drive to explore and expand. We are a species that has never been content to remain in one place. From our origins in Africa, humans have spread to every continent, adapted to every environment from deserts to Arctic tundra. The settlement of the Pacific Islands represents one of humanity's most remarkable achievements, as Polynesian navigators crossed vast oceanic distances in outrigger canoes, establishing new societies on tiny, isolated specks of land. An interstellar highway system would enable this same pioneering spirit on a cosmic scale. But could such a system actually revolutionize interstellar travel the way roads revolutionized terrestrial travel? The comparison is apt, but requires careful consideration. Roads revolutionized travel by providing several key advantages. They created standardized, maintained pathways that were faster and safer than traveling across raw terrain. They enabled predictable travel times, which facilitated trade and planning. They could be used by anyone with a suitable vehicle, not just experts in navigation. They concentrated traffic, which led to the development of services along the routes such as inns, repair facilities, and trading posts. And they created network effects, where the value of the system increased as more roads were added and more people used them. An interstellar highway system could provide similar advantages. Established routes would incorporate the most efficient trajectories, accounting for gravitational assists from planets or stars along the way. These routes would be mapped in exquisite detail, with hazards identified and avoided. Navigation would become standardized, with beacons or markers guiding vessels along the optimal path. Infrastructure along these routes would transform the travel experience. Imagine waypoints positioned at strategic locations, perhaps around particular stars or in deep space. These could serve multiple functions. They could provide refueling, either through harvested local resources or stockpiled supplies. They could offer repair facilities for damaged vessels. They could serve as communication relays, allowing messages to propagate along the network. They could house emergency shelters for crews in distress. They could even serve as gravitational catapults, using massive structures to accelerate vessels without requiring them to carry as much fuel. The standardization of vessel designs would naturally follow. Just as the width of Roman roads influenced the design of carts and wagons, and just as modern highway systems led to standardized automobile designs, interstellar highways would likely lead to optimized vessel designs suited for these particular routes. This standardization would reduce costs, improve safety, and accelerate technological development, as improvements could be rapidly disseminated across the fleet. Perhaps most importantly, an interstellar highway system would create positive feedback loops. As routes became established and infrastructure built, travel along these routes would become easier and cheaper. This would encourage more travel, which would justify additional infrastructure investment, which would further reduce costs and difficulties. Eventually, what began as difficult, expensive, and dangerous journeys would become routine. Consider how this transformed terrestrial travel. In the early 1800s, traveling from New York to Chicago was a major expedition requiring weeks of difficult travel through wilderness. By the late 1800s, with the railroad built, the same journey took a day or two in relative comfort. By the mid-20th century, with highways and cars, it was a leisurely road trip. By the late 20th century, it was a 2-hour flight. Each improvement in infrastructure made the journey faster, cheaper, safer, and more routine. We can imagine a similar progression for interstellar travel. The first journeys to nearby stars would be generation ships, taking centuries and requiring enormous resources. With improved propulsion technology, perhaps using fusion or matter-antimatter reactions, travel times might drop to decades. With an established highway system, including waypoints for refueling and gravitational assists from optimally positioned infrastructure, travel times might drop further to years. Eventually, if truly revolutionary technologies like warp drives or wormholes prove possible, travel times might drop to weeks or even days. But there are also significant differences between terrestrial highways and interstellar ones that we must acknowledge. The most obvious is the sheer scale. The longest terrestrial road journey is perhaps 30,000 miles if you drive from the northern tip of Alaska to the southern tip of South America. The nearest star is about 25 trillion miles away, roughly 1 billion times farther. This creates challenges that have no terrestrial equivalent. At these distances, communication becomes problematic. A message sent at light speed to Proxima Centauri takes more than 4 years to arrive, and another 4 years for a response. This makes real-time coordination impossible. Any infrastructure along an interstellar highway would need to operate autonomously or with pre-programmed instructions, unable to call back to Earth for guidance on unexpected situations. The energy requirements are also staggering. A typical car might require 50 gallons of gasoline to drive 1,000 miles. Accelerating even a small spacecraft to a significant fraction of light speed requires energy equivalent to many nuclear weapons. Carrying this energy, whether as fuel or generated through other means, is one of the fundamental challenges of interstellar travel. While an interstellar highway system could potentially help through refueling waypoints or external propulsion systems, the basic energy requirements remain daunting. The timescales involved also differ fundamentally from terrestrial travel. A road trip across America might take a few days. Even the longest ocean voyages historically took months. But interstellar journeys, even along optimized routes with advanced technology, would likely take years at minimum, possibly decades or centuries. This creates biological challenges for human travelers, potentially requiring generation ships, suspended animation, or other solutions not needed for terrestrial journeys. Despite these challenges, the concept of an interstellar highway system represents a crucial shift in thinking about space exploration. Instead of treating each mission as a unique venture into the unknown, we begin to think in terms of infrastructure, networks, and systems. We think not just about reaching a destination, but about creating sustainable, reusable pathways that others can follow. This shift in thinking has historical precedent. Early ocean voyages of exploration were dangerous, unpredictable affairs with high mortality rates. Magellan's expedition lost 4 of its 5 ships and nearly 90% of its crew. But these voyages established routes, and subsequent journeys along these routes became progressively safer and more routine. Eventually, regular commercial shipping followed these routes, and the age of exploration gave way to an age of global trade and cultural exchange. We stand now at a similar threshold regarding interstellar space. The first missions to nearby stars will be extraordinary efforts, perhaps taking decades to plan and execute, with uncertain outcomes. But if we can think beyond individual missions to the creation of infrastructure and systems, we can envision a future where interstellar travel becomes not an extraordinary achievement, but a routine part of civilization's activities. An interstellar highway system could be the framework that transforms humanity from a single planet species to a true spacefaring civilization, with outposts, colonies, and eventually independent societies orbiting different stars, all connected by these cosmic roads. Just as ancient highways helped unify empires and modern highways helped integrate economies, interstellar highways could help maintain unity and cooperation across distances that would otherwise isolate communities for generations. The construction of such a system would be the work of centuries, perhaps millennia. It would require international cooperation, sustained investment, and technological breakthroughs we can barely imagine today. But the same was true of every great infrastructure project in history. The Great Wall of China took centuries to build. The Gothic cathedrals of Europe sometimes took 200 years to complete. The settlement of the Pacific took generations of Polynesian navigators. These ancestors undertook projects whose completion they would never see, building for futures they could only imagine. Perhaps we are the generation that begins to think seriously about interstellar highways, even if their completion lies far in our future. Perhaps our contribution is not to build these systems ourselves, but to begin the intellectual and technological groundwork that makes them possible for our descendants. Perhaps our legacy will be that we saw beyond individual missions to the stars and envisioned instead a network, a system, a true infrastructure for cosmic civilization. The road ahead is long, spanning not miles but light years. But every great journey begins with a single step, and every great highway system begins with a vision of connection across distance. The interstellar highway system remains, for now, a concept, a dream, a possibility hovering at the edge of technological feasibility. But it is a dream worth pursuing, because it represents not just a means of travel, but a vision of humanity's future among the stars, connected rather than isolated, united by cosmic roads that span the darkness between distant suns. When we gaze up at the night sky, the stars seem close enough to touch, scattered like diamonds across velvet darkness. This illusion has captivated humanity for millennia, inspiring myths, navigation, and dreams of exploration. But the universe guards its secrets behind a barrier far more formidable than any ocean or mountain range. The barrier of distance and the fundamental laws of physics that govern how fast anything can move through space. To understand why we need revolutionary concepts like interstellar highway systems, we must first confront the sobering reality of our current limitations. Space travel, despite decades of advancement and spectacular achievements, remains confined to our cosmic backyard. We have sent humans to the moon just 238,000 miles away. We have sent robotic probes to the outer planets of our solar system, billions of miles from Earth. Yet even our most distant artificial object, Voyager 1, launched in 1977 and traveling at roughly 38,000 miles per hour, has barely begun to leave our solar system after nearly 50 years of continuous travel. Voyager 1 is currently about 14.5 billion miles from Earth, making it the most distant human-made object in existence. This seems like an impressive distance until you realize that this is still within what astronomers call the heliosphere, the region of space dominated by the Sun's influence. The true boundary of our solar system, marked by the Oort cloud, a vast shell of icy objects orbiting far beyond the planets, extends roughly 1 light-year from the Sun. At its current speed, Voyager 1 will not escape this region for another 30,000 years. Let that sink in for a moment. Our fastest spacecraft, traveling for 30,000 years, will only just barely leave our solar system, and that is before attempting to reach another star. The nearest star system to our Sun is Alpha Centauri, a triple star system located 4.37 light-years away. One of these stars, Proxima Centauri, is slightly closer at 4.24 light-years. To put this in more tangible terms, a light-year is the distance light travels in 1 year, moving at 186,000 miles per second. This works out to approximately 5.88 trillion miles per light-year. Proxima Centauri is therefore roughly 25 trillion miles from Earth. How long would it take to reach Proxima Centauri with current technology? The answer is profoundly discouraging. If we use conventional chemical rockets, like those that powered the Apollo missions to the moon, we are looking at travel times exceeding 50,000 years. Even with more advanced ion propulsion systems, which provide continuous low thrust over long periods, the journey would still take thousands of years. The Voyager probes, moving at about 17 kilometers per second relative to the Sun, would require approximately 75,000 years to traverse this distance if they were headed in that direction, which they are not. These numbers reveal the first and most fundamental limitation of current space travel: speed. Chemical rockets, which work by expelling hot gas at high velocity to generate thrust, are limited by the energy content of their fuel and the weight they must carry. The tyranny of the rocket equation, first formulated by Russian scientist Konstantin Tsiolkovsky in 1897, shows that the amount of fuel needed increases exponentially with desired speed. To go faster, you need more fuel, but more fuel means more weight, which means you need even more fuel to accelerate that additional weight, and so on in a vicious cycle. For a rocket carrying its own fuel, there comes a point where adding more fuel provides diminishing returns. Current chemical rockets can achieve speeds of perhaps 50 to 60 kilometers per second, about 0.02% of the speed of light. This is simply not fast enough for practical interstellar travel. The second major limitation is energy. The amount of energy required to accelerate a spacecraft to a significant fraction of light speed is staggering. To accelerate even a small probe weighing 1 ton to 10% of light speed would require energy equivalent to hundreds of nuclear weapons. Where does this energy come from? How is it stored or generated? How is it converted into motion? These questions have no easy answers with current technology. The third limitation is protection. Space is not empty. Even the near vacuum of interstellar space contains atoms, mostly hydrogen, along with dust particles and cosmic rays. At conventional spacecraft speeds, these pose minimal threat, but at relativistic speeds, approaching a significant fraction of light speed, even individual atoms become deadly projectiles. A spacecraft traveling at half the speed of light would experience collisions with interstellar hydrogen atoms with energies comparable to particle accelerator collisions. A dust grain, nearly harmless at low speeds, becomes a devastating impactor. The accumulated radiation exposure over years of travel would be lethal to unshielded humans. The fourth limitation is time. Even if we could build a spacecraft capable of reaching 10% of light speed, an optimistic goal with speculative technologies, the journey to Proxima Centauri would still take 43 years. Add time for acceleration and deceleration, and you are looking at 50 years or more. This is longer than most careers, a significant fraction of a human lifetime. For more distant stars, the problem multiplies. A star 50 light-years away would require 500 years of travel time at 10% of light speed. The fifth limitation is communication. Once a spacecraft leaves Earth, communication becomes increasingly difficult. Radio signals travel at light speed, which sounds fast until you consider the distances involved. A signal from Proxima Centauri takes 4.2 years to reach Earth, and another 4.2 years for a response. A conversation is impossible. Instructions from mission control cannot guide real-time decisions. A spacecraft traveling to another star must be largely autonomous, capable of handling unexpected situations without help from home. The sixth limitation is biological. Humans are not designed for multi-decade or multi-century journeys through space. We need food, water, air, and waste recycling. We need gravity or our bones weaken and our muscles atrophy. We need protection from radiation. We need psychological stimulation and social interaction. Generation ships, vessels designed to house multiple generations of travelers, could theoretically solve some of these problems, but they introduce new challenges around maintaining technology and social cohesion over centuries. Given these formidable limitations, humanity's reach into the cosmos has remained limited to our solar system. We have achieved remarkable things within this boundary, landing humans on the Moon, sending rovers to Mars, flying by Pluto, studying the outer planets and their moons. But crossing the gulf between stars requires not incremental improvements to existing technology, but revolutionary breakthroughs. This brings us to the theoretical methods that could make interstellar travel practical. These range from ambitious but potentially achievable with future technology to speculative concepts that may require physics we do not yet understand. The most straightforward approach is simply to go faster using advanced propulsion systems. Nuclear pulse propulsion, first seriously studied in Project Orion during the 1950s and 60s, involves detonating nuclear weapons behind a spacecraft and riding the blast wave. This sounds dangerous and crude, but the physics is sound. Such a system could theoretically achieve speeds of 3 to 5% of light speed, reducing the journey to Proxima Centauri to perhaps a century or less. A more elegant nuclear approach is fusion propulsion. While we have not yet achieved sustained, controlled fusion power on Earth, the potential is enormous. Fusion reactions, combining light elements like hydrogen isotopes into heavier elements and releasing tremendous energy, could provide specific impulses far exceeding chemical rockets. A fusion rocket might achieve 10 to 15% of light speed, bringing Proxima Centauri within a 40 to 50-year journey. Even more ambitious is antimatter propulsion. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation E equals mc squared. This is the most efficient energy release possible under known physics. Unfortunately, antimatter is extraordinarily difficult to produce and store. Current production rates measure in nanograms per year, and costs are astronomical, estimated at trillions of dollars per gram. Nevertheless, if these challenges could be overcome, antimatter propulsion could potentially achieve speeds of 50% of light speed or higher. Another approach entirely abandons carrying fuel and instead uses external power sources. Laser sail propulsion involves using enormous laser arrays, perhaps based in orbit around the Sun or Moon, to accelerate lightweight spacecraft equipped with ultra-thin reflective sails. The lasers push against the sail continuously as the spacecraft accelerates away from the solar system. The Breakthrough Starshot Initiative, announced in 2016, proposed using this method to send small probes to Alpha Centauri within 20 years, achieving 20% of light speed. The challenges are immense, requiring laser powers measured in gigawatts and sails that are both incredibly thin and incredibly strong. But the physics is straightforward. These methods, while ambitious, all remain within the bounds of known physics. They represent engineering challenges rather than fundamental impossibilities. Given sufficient resources, time, and technological development, any of them could potentially be realized. But what if we want to go faster? What if we want to approach or even exceed the speed of light? This brings us into much more speculative territory, requiring either exploitation of physics loopholes or entirely new physics. The speed of light, approximately 300 million meters per second, is not just a speed limit in the conventional sense. According to Einstein's special theory of relativity, published in 1905, it is a fundamental feature of the universe's structure. As objects with mass approach light speed, several things happen. Their mass effectively increases, requiring ever more energy to accelerate further. Time slows down for them relative to stationary observers. Distances in their direction of travel appear to contract. These are not engineering limitations, but fundamental physical laws, verified by countless experiments over more than a century. For an object with mass to actually reach light speed would require infinite energy, which is clearly impossible. This seems to slam the door on faster-than-light travel, and indeed for conventional propulsion methods it does. But some physicists have identified potential loopholes or alternative approaches that might circumvent this limitation without violating relativity. The most famous of these is the Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994. This concept is inspired by science fiction but based on real physics. The idea is not to move the spacecraft through space faster than light, which relativity forbids, but to move space itself around the spacecraft. Imagine space as a flexible fabric. The warp drive would compress space in front of the spacecraft and expand it behind, creating a warp bubble that carries the spacecraft along. From the perspective of someone inside the bubble, they are stationary, but relative to the rest of the universe, the bubble, and thus the spacecraft, moves faster than light. This is analogous to being on a moving walkway at an airport. You are walking at normal speed relative to the walkway, but moving faster relative to the terminal around you. The mathematics of general relativity, Einstein's theory of gravity and curved space-time, allows for such a configuration. It does not violate relativity because nothing is actually moving through space faster than light. Instead, space itself is moving. However, there are enormous problems with this idea. First, the amount of energy required is staggering, initially calculated to be equivalent to the mass energy of Jupiter. Later refinements have reduced this estimate, but it remains far beyond anything we can imagine generating. Second, the energy would need to be negative energy, or more precisely, exotic matter with negative energy density. Such matter has never been observed and may not exist. Third, even if we could create a warp bubble, it is unclear how we could control it from inside. The region inside the bubble would be causally disconnected from its edge, meaning no signal from inside could reach the boundary to adjust the warp field. Fourth, there are concerns about what happens when the warp drive is turned off. Some calculations suggest that the energy accumulated at the front of the bubble during faster-than-light travel would be released as deadly radiation when the ship drops back to normal space, possibly destroying whatever destination the ship was approaching. Despite these problems, research continues. Some physicists have proposed modified warp drive geometries that might reduce energy requirements or use more plausible forms of energy. The concept remains speculative, but not completely dismissed as impossible. Another approach to faster-than-light travel involves wormholes, hypothetical tunnels through space-time that connect distant regions of the universe. If a wormhole could be created or found connecting our solar system to Alpha Centauri, traveling between the stars would be as simple as stepping through a doorway. Wormholes emerge naturally from the mathematics of general relativity. They were first studied seriously by physicists Albert Einstein and Nathan Rosen in 1935, leading to their technical name, Einstein-Rosen bridges. However, the wormholes predicted by these equations have problems. They exist for only an instant before collapsing. They are incredibly small, far smaller than an atom, and they are one-way only, not traversable. To create a traversable wormhole, one that a spacecraft could actually pass through, requires exotic matter with negative energy density, the same problematic material needed for warp drives. Even if such a wormhole could be created, keeping it stable and large enough for a spacecraft would require amounts of exotic matter that make the warp drive requirements look modest. There are also causality problems. Some wormhole configurations could theoretically be used as time machines, allowing travel into the past. This creates paradoxes that suggest the universe may have built-in protections against such configurations, though how this protection works remains unclear. A third speculative approach is hyperspace travel, popularized in science fiction. The idea is that our universe might be embedded in a higher dimensional space, like a two-dimensional surface curved through three-dimensional space. If we could somehow enter this higher dimensional realm, distances that are vast in our normal three-dimensional space might be much shorter through hyperspace. This concept has some basis in modern physics. String theory and other attempts to unify quantum mechanics and general relativity often propose extra dimensions beyond the three spatial dimensions we experience. However, these extra dimensions are theorized to be incredibly tiny, curled up at scales trillions of times smaller than an atom. There is no known mechanism for entering or utilizing these dimensions for travel, and no observational evidence that they exist at all. Other speculative concepts include quantum tunneling on a macroscopic scale, manipulation of the quantum vacuum, or exploitation of other exotic physics. All of these share a common feature. They require physics we do not currently understand and may not even be possible. So where does this leave us regarding the possibility of an interstellar highway system? The answer depends on which technologies prove feasible. If we are limited to known physics and conventional propulsion, even advanced nuclear or antimatter rockets, then an interstellar highway would be a network of centuries-long journeys. Infrastructure like way stations, navigation beacons, and communication relays would be essential, but the system would operate on timescales of generations. Travelers would need suspended animation, generation ships, or would need to accept that they are making a one-way journey their descendants will complete. Such a system is technically possible, but would require extraordinary social organization and commitment. It would resemble less a modern highway and more the generational voyages of Polynesian seafarers, where crews departed, knowing they might never return, hoping to establish new homes for their children or grandchildren. If laser sail technology or other light-speed propulsion methods prove practical, journey times could drop to decades. This is still a significant fraction of a human lifetime, but not impossible. A person might depart Earth as a young adult and arrive at a distant star as a middle-aged or elderly person. Infrastructure becomes more valuable in this scenario because repair and refueling stations could meaningfully assist journeys that last decades rather than centuries. If warp drives, wormholes, or other faster-than-light methods prove possible, the game changes completely. Journey times could potentially drop to years, months, weeks, or even days. An interstellar highway system would begin to resemble our terrestrial highways, with travel times short enough that individual beings could make multiple trips in their lifetimes. Infrastructure would serve the same purposes as on Earth: safety, efficiency, convenience. The most likely near-term scenario involves a hybrid approach. Initial exploration and colony establishment would use slower but more proven technologies: fusion rockets, laser sails, or advanced ion drives. These would establish the first outposts around nearby stars over the course of the next few centuries. As technology advances, faster methods would gradually replace slower ones. Just as jet aircraft replaced propeller planes, which replaced ships, which replaced walking. Each generation would push a little farther, move a little faster, until eventually a true network of rapid interstellar travel becomes possible. The first highway might connect our solar system to Alpha Centauri, a single route taking decades to traverse. Later highways might reach dozens of stars within 50 light-years, with journey times dropping to years. Eventually, if revolutionary physics proves possible, the highway system might span thousands of light-years, connecting an empire of humanity among the stars. The fundamental point is this: interstellar travel is not impossible. It is extraordinarily difficult with current technology, requiring journey times that challenge human biology and social organization. But the laws of physics do not forbid it. Given sufficient time, resources, and determination, even the vast gulfs between stars can be crossed. And once crossed, they can be crossed again, more efficiently each time, until pathways become routes, routes become highways, and highways become the foundation of a cosmic civilization. When ancient Polynesian navigators set out across the Pacific Ocean, they did not travel randomly. They followed routes determined by winds, currents, and the positions of islands that could serve as waypoints. They read the stars, the waves, and the flight patterns of birds. They passed down knowledge of these routes through generations, encoding navigation instructions in chants and stories. These routes were not visible lines drawn on the ocean's surface, but rather patterns of natural forces and strategic waypoints that made certain paths more favorable than others. Similarly, an interstellar highway system would not consist of physical roads through space, but rather carefully chosen routes that take advantage of natural forces, minimize energy expenditure, and provide the safest and most efficient paths between stars. Understanding what determines these routes requires us to think about space not as empty void, but as a dynamic environment filled with gravitational fields, radiation, dust, and other features that can either aid or hinder travel. The first and most obvious factor determining interstellar routes would be simple geometry. The straight line distance between stars. In the absence of other considerations, the shortest path between 2 points is a straight line. If we lived in a universe with no gravity, no obstacles, and unlimited energy, our interstellar highways would simply connect stars in straight lines, like roads drawn across a flat plane. But the universe is not so simple. Space is pervaded by gravitational fields from stars, planets, and other massive objects. These fields curve space itself, meaning that the shortest path between 2 points is not actually a straight line, but a curved trajectory called a geodesic. This is similar to how the shortest path between 2 cities on Earth's curved surface is not a straight line through the planet, but a curve along the surface called a great circle route. Gravity would play a crucial role in determining interstellar routes for another reason: gravitational assists. When a spacecraft passes close to a planet or star, it can use that object's gravity to change its speed and direction without expending fuel. This technique has been used extensively in our solar system. The Voyager probes used gravitational assists from Jupiter and Saturn to reach the outer solar system. The Parker Solar Probe uses repeated gravitational assists from Venus to gradually lower its orbit closer to the Sun. For interstellar travel, gravitational assists could be even more valuable. A spacecraft leaving our solar system could use Jupiter or Saturn to gain additional velocity, essentially getting a free push from the giant planets. Similarly, when approaching a destination star system, gravitational assists from planets or the star itself could help with deceleration, reducing the fuel needed to slow down and enter orbit. This means that optimal interstellar routes would not necessarily be straight lines between stars, but curves that pass near massive objects, positioned to provide helpful gravitational boosts. The routes would resemble the trajectory of a pinball, bouncing from one gravitational influence to another, each interaction carefully calculated to maximize efficiency. But there is an even more profound way that gravity could determine interstellar routes: the existence of what some scientists call the interplanetary transport network, or gravitational highways. These are not highways in the conventional sense, but rather pathways through space where gravitational forces from multiple bodies balance in specific ways, creating what mathematicians call Lagrange points and associated manifolds. Lagrange points are positions in space where the gravitational pull of two large bodies, like the Sun and Jupiter, exactly balance the centrifugal force felt by a smaller object, like a spacecraft. There are 5 such points for any two-body system. 3 of them are unstable, meaning that an object placed there will eventually drift away. But this instability can be exploited for low-energy transfers between different orbital regions. The paths connecting these Lagrange points through space form a complex network of routes that require minimal energy to traverse. Spacecraft can ride these gravitational superhighways like rivers flowing through space, moving between different regions of the solar system with very little fuel expenditure. The price paid for this efficiency is time. These low-energy routes are slow, taking months or years instead of weeks. For interstellar travel, similar structures might exist on a larger scale. The gravitational interaction between our Sun and nearby stars, or between stars and the galactic center, could create analogous pathways. These would be even slower than their solar system counterparts, but for civilization with patience and a long-term perspective, they could provide energy-efficient routes for cargo, resources, or non-urgent travelers. Imagine a network of routes threading through local stellar neighborhood, taking advantage of these gravitational structures. Ships carrying passengers or urgent cargo might take faster, more direct routes requiring more energy, but bulk freighters carrying raw materials or non-perishable goods might take the slow gravitational highways, drifting along energy-efficient paths that take centuries but cost almost nothing in fuel. Beyond gravity, a second major factor determining interstellar routes would be obstacles and hazards. Space is not uniformly empty. Some regions contain dense molecular clouds, areas where gas and dust concentrate. These clouds are nurseries for new stars, but they would be dangerous for spacecraft traveling at high speeds. Even thin gas becomes a serious problem at relativistic velocities. A spacecraft traveling at 10% of light speed encounters interstellar hydrogen atoms with kinetic energies, equivalent to particle accelerator collisions. At 50% of light speed, these collisions become catastrophic. A ship traveling through a dense molecular cloud at such speeds would be quickly eroded, its hull degrading under constant bombardment, its crew exposed to deadly radiation. Therefore, interstellar routes would need to avoid dense regions of gas and dust, threading through the thinner regions of interstellar space. Maps of the local interstellar medium, showing the distribution of gas, dust, and magnetic fields, would be essential planning tools. Routes might curve around molecular clouds the way terrestrial roads curve around mountains or swamps, choosing the path of least resistance even if it is not the shortest distance. Radiation presents another hazard. Cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, pervade space. Their intensity varies depending on location and the local magnetic field environment. Some regions of space are more protected from cosmic rays than others. Routes might preferentially pass through regions where the stellar wind or magnetic fields provide some natural shielding. Similarly, routes would avoid passing too close to dangerous objects, active pulsars with their beams of radiation, regions where supernovae are likely, or black holes whose tidal forces could damage or destroy a spacecraft. While these dramatic hazards are relatively rare, a well-planned interstellar highway would identify and route around them. A third factor determining routes would be the location of resources and infrastructure. Just as terrestrial highways connect cities and pass through areas where services are available, interstellar highways would connect inhabited systems and pass near waypoints where resources can be obtained. A star system with established colonies would naturally become a hub in the network, with routes converging on it from multiple directions. Even uninhabited systems might become waypoints if they contain useful resources. Ice-rich comets for water and fuel, asteroid fields for metals, gas giants for fusion fuel. The concept of resource corridors would become important. A route that passes near a star system where fusion fuel can be easily harvested becomes more valuable than an equally fast route through empty space. Over time, infrastructure would be built at strategic locations along major routes: fuel depots, repair facilities, communication relays, and refugees for ships in distress. These waypoints would transform the nature of interstellar travel. Instead of each journey being a single enormous leap across light years, it could be broken into stages, like a road trip with rest stops. A ship might travel from Earth to a waypoint 1 light year out, refuel and undergo maintenance, then continue to a second waypoint, and so on until reaching its destination. Each individual stage would be more manageable than the full journey. The placement of waypoints would influence route selection. A slightly longer route that passes near 2 waypoints might be preferable to a shorter route through empty space, just as drivers often choose highways with rest stops over shorter roads without services. A fourth factor would be stellar motion. Stars are not stationary. They orbit the galactic center on different paths and at different speeds. Our Sun, for instance, travels around the galaxy at roughly 500,000 miles per hour, completing one orbit every 230 million years. Other nearby stars have their own distinct motions relative to us. This means that the distance between stars changes over time. Alpha Centauri is currently 4.24 light-years away and getting closer, approaching at about 12 miles per second. In about 27,000 years, it will reach its closest approach at around 3 light-years, then begin moving away. Other stars are moving even faster relative to us. For planning interstellar routes, stellar motion matters. A journey to a star 50 light-years away, taking decades or centuries to complete, must account for where that star will be when the spacecraft arrives, not where it is when the ship departs. This is similar to how you must lead a moving target when throwing a ball. You aim not at where the target is, but where it will be. The optimal route is therefore not toward the star's current position, but toward the point in space where the star will be at the calculated arrival time. This requires precise knowledge of stellar positions and velocities. As stellar neighborhood changes over millennia with stars moving relative to each other, the optimal routes change as well. The interstellar highway map must be continuously updated. On even longer timescales, stellar motions could dramatically alter the structure of the highway network. Stars currently close to us will drift away. Other stars will approach. In 50,000 years, the stellar neighborhood will look quite different. In 1,000,000 years, it will be unrecognizable. An interstellar civilization must adapt its highway network to these changing conditions, perhaps abandoning routes to stars that have moved too far away, and establishing new routes to stars that have drifted closer. This brings us to the speculative possibilities. Could exotic features of space-time itself determine interstellar routes? If wormholes exist, they would obviously define the most important routes, reducing journeys of light years to trips through a tunnel in space-time. The locations of wormhole mouths, if they could be found or created, would become the most valuable real estate in the galaxy, like major ports in terrestrial commerce. A civilization with the technology to create or move wormholes could design their highway network with godlike power, placing wormhole mouths wherever travel is needed. Want to connect two distant colonies? Create a wormhole between them. Need to access resources in a distant star system. Thread a wormhole there. The network topology would be limited only by the energy and technology available for wormhole manipulation. Similarly, if regions of space exist where the warp drive equations have solutions requiring less exotic energy, or where the vacuum energy density is different, these regions might become preferred corridors for faster-than-light travel. This is highly speculative, as we have no evidence such regions exist, but if they do, they would define natural highways just as surely as valleys between. Mountains define paths for terrestrial roads. Some physicists have even speculated about cosmic strings, hypothetical, one-dimensional defects in space-time left over from the early universe. If cosmic strings exist, and if their gravitational properties are suitable, they could potentially be used for propulsion or navigation. A spacecraft might follow along a cosmic string, using its unusual properties to achieve high velocities. Again, this is purely speculative, but it illustrates how undiscovered features of space-time might determine routes. Regardless of which factors prove most important, actually navigating these interstellar routes presents its own challenges. On Earth, navigation evolved from dead reckoning and landmark recognition to compass bearings and sextant measurements, to GPS satellites providing precise positioning. Interstellar navigation would require analogous tools scaled up to cosmic distances. The most fundamental navigation tool would be precise maps of stellar positions. We already have such maps, compiled by missions like the European Space Agency's Gaia satellite, which has measured the positions and motions of over 1 billion stars with unprecedented accuracy. These maps provide the framework for navigation, the fixed reference points against which a spacecraft's position can be determined. But knowing the stars' positions is not enough. The spacecraft must also know its own position relative to those stars. At interstellar distances, this becomes challenging. Earth-based tracking, which works well for probes in our solar system, becomes impractical. Radio signals from a spacecraft near Alpha Centauri would take over 4 years to reach Earth, and another 4 years for a response. Real-time tracking is impossible. Instead, spacecraft would need autonomous navigation systems, essentially interstellar versions of GPS. One approach is pulsar navigation. Pulsars are rapidly rotating neutron stars that emit beams of radio waves with extraordinary regularity, like cosmic lighthouses. Each pulsar has a unique rotation period and pulse pattern. By detecting multiple pulsars and measuring their pulse arrival times, a spacecraft can triangulate its position in three-dimensional space to high precision. This technique has already been tested. NASA's NICA instrument on the International Space Station successfully used pulsar signals to determine its position in 2017. For interstellar travel, pulsar navigation could provide continuous, autonomous positioning without needing contact with Earth. A spacecraft could know exactly where it is going, and how to adjust its course using only pulsar signals and its own instruments. Other navigation aids could include beacons placed along established routes. These beacons might be as simple as radio transmitters broadcasting their precise positions, allowing spacecraft to triangulate their location, or they might be more sophisticated, providing navigation data, route updates, hazard warnings, and other information to passing ships. As the highway network matured, these beacons would multiply, creating a dense navigational infrastructure similar to the system of buoys, lighthouses, and channel markers that guide ships through coastal waters on Earth. A spacecraft traveling an established route would never be out of range of navigation beacons, ensuring it could always determine its position accurately and receive up-to-date routing information. The communication infrastructure would be equally important. The vast distances of interstellar space make real-time communication impossible due to light speed delay. But delayed communication is still valuable. A network of communication relays along major routes could ensure messages eventually reach their destinations, even if delayed by years. This network would serve multiple purposes beyond simple communication. It could propagate navigation updates, warn of newly discovered hazards, coordinate traffic in busy systems, and provide emergency communication for ships in distress. It would be the interstellar equivalent of the maritime radio network or air traffic control, ensuring that even though ships are physically isolated in the depths of space, they remain informationally connected to the broader civilization. The actual process of flying an interstellar route would combine automated systems with human or artificial intelligence oversight. For most of a journey, the spacecraft would follow a pre-calculated trajectory, making small corrections as needed to stay on course. Automated systems would continuously monitor the ship's position using pulsar navigation or other methods, compare it to the planned route, and make minor adjustments to the trajectory. Hazard avoidance would be partly automated and partly reliant on pre-existing knowledge. Maps of dust clouds, radiation sources, and other hazards would be stored in the ship's computer. The ship would automatically avoid mapped hazards. If an unmapped hazard was detected, perhaps a previously unknown dust cloud or an unexpected radiation source, the ship would take evasive action and transmit information about the new hazard back along the route so that future ships could be warned. For journeys lasting decades or centuries, course corrections would become increasingly important. Even tiny errors in the initial trajectory, if uncorrected, would compound over time, potentially causing the spacecraft to miss its destination by huge distances. Imagine aiming at a target 4 light-years away and being off by just 1 part per billion in your initial direction. By the time you traveled 4 light-years, you would miss your target by over 200,000 miles, more than the distance from Earth to the Moon. Continuous navigation and course correction would be essential. The spacecraft would regularly check its position, verify it is still on the correct trajectory, and make adjustments as necessary. This is similar to how modern aircraft continuously adjust their course during long flights, compensating for winds and other factors that would otherwise push them off their planned route. As an interstellar highway network developed, the routes would gradually be refined through experience. The first ships to travel a route would gather data on conditions along the way, actual dust density, radiation levels, gravitational influences, and other factors. This information would be transmitted back, allowing route planners to refine the trajectory for future missions. Over many missions, the routes would be optimized the way terrestrial roads are gradually improved. Dangerous sections would be rerouted around. More efficient trajectories would be discovered through trial and experience. Waypoints would be positioned at the most useful locations. What began as rough paths would evolve into well-mapped, well-maintained highways with known characteristics and predictable travel times. The accumulated knowledge of thousands of journeys would be encoded in the navigation databases carried by every ship. A captain planning a journey from Earth to Tau Ceti, 12 light-years away, would consult these databases to choose the optimal route. The database might suggest a path that curves slightly to take advantage of a gravitational assist from a brown dwarf 2 light-years out, then passes near an established waypoint at 6 light-years for refueling, before continuing to Tau Ceti. The database would include detailed information about every segment of the route, expected travel time, fuel requirements, hazards to avoid, communication relay positions, emergency refuge locations, and historical data about conditions along the path. It would be continuously updated with reports from ships currently traveling the route, ensuring the information remains current. This infrastructure of knowledge, even more than physical waypoints and beacons, would transform interstellar travel from random voyages into the unknown, to routine transits along well-understood routes. The first explorers to cross the space between stars would be pioneers in the truest sense, venturing into complete uncertainty. But their successors would be more like truckers or airline pilots, following established routes and procedures, confident in their knowledge of the path ahead. The selection and mapping of interstellar routes would ultimately be determined by a combination of all these factors: geometry and distance, gravitational fields and assists, resources and infrastructure, stellar motion and hazard avoidance. Like terrestrial road networks, which wind through geography, following paths of least resistance and greatest utility, interstellar highways would thread through the three-dimensional geography of local space, connecting stars along routes that balance efficiency, safety, and practicality. And like terrestrial highways, the network would grow organically over time. The first routes would connect the Sun to the nearest stars: Alpha Centauri, Barnard's Star, Wolf 359. As these routes matured and colonies were established, new routes would branch out from those colonies to nearby stars, gradually expanding the network in all directions. Eventually, thousands of routes would crisscross our galactic neighborhood, connecting hundreds of star systems in a web of commerce, communication, and cultural exchange. Standing on Earth today, looking up at the night sky, these highways do not yet exist except in imagination, but the stars are there. The distances between them are fixed by the geometry of space, and the natural forces that would determine optimal routes already exist, waiting to be mapped and exploited. The highways are latent in the structure of our stellar neighborhood, invisible but real, waiting for a spacefaring civilization to discover and chart them. When the Roman Empire decided to build its network of roads spanning 3 continents, it faced a monumental challenge. Workers had to quarry stone, level terrain, bridge rivers, tunnel through mountains, and maintain these roads across thousands of miles through diverse climates and hostile territories. The project required the labor of millions over centuries, consumed vast resources, and demanded innovations in engineering, logistics, and organization. Yet the Romans succeeded, creating infrastructure that lasted millennia and enabled the rise of one of history's greatest civilizations. Building an interstellar highway system would make Roman road construction look like a weekend gardening project. The scale, the challenges, the resources required, and the timeframes involved would dwarf any infrastructure project in human history. Yet if we are serious about becoming an interstellar species, about creating a true network connecting star systems, we must grapple with the practical question: what would this infrastructure actually consist of, and how could it possibly be built? The first thing to understand is that an interstellar highway system would not be a single type of infrastructure, but rather multiple interconnected systems, each serving different purposes. Like terrestrial highway systems, which include not just the roads themselves, but also bridges, rest stops, gas stations, repair shops, traffic signals, emergency call boxes, and maintenance depots, an interstellar highway would be a complex ecosystem of different facilities and technologies. At the most fundamental level, the infrastructure would include navigation beacons. These would be the interstellar equivalent of road signs and mile markers, helping spacecraft know where they are and ensuring they stay on the correct route. A navigation beacon might be as simple as a radio transmitter, broadcasting a unique identification code and precise timing signal, allowing spacecraft to triangulate their position by receiving signals from multiple beacons. These beacons would need to be positioned at strategic intervals along routes, perhaps every 10th of a light year or so, close enough that a spacecraft could always detect multiple beacons for accurate positioning. For a route spanning just the 4.24 light-years to Alpha Centauri, this would require dozens of beacons. For a network connecting hundreds of stars across hundreds of light-years, thousands of beacons would be needed. Each beacon would need to be autonomous, operating for decades or centuries without maintenance. It would need a power source, likely a small nuclear reactor or radioisotope generator, as solar panels would be useless in the darkness between stars. It would need radiation-hardened electronics capable of withstanding cosmic rays and micrometeorite impacts. It would need enough intelligence to self-diagnose problems adjust its broadcast parameters if needed, and report its status back along the network. The positioning of these beacons would itself be a challenge. They cannot simply be placed in space and left stationary, because nothing in space is truly stationary. Everything orbits something else. A beacon placed between stars would orbit the galactic center, just as stars do, but its orbital path might differ from the stars it is meant to guide traffic between. Over time, stellar motion would carry stars away from the beacons, requiring the beacons to be moved or replaced. One solution would be to place beacons in orbit around specific objects. Small stars, brown dwarfs, large planets, or even asteroids along the route. This would anchor the beacons to something, though their positions would still change as their host objects move. Alternatively, beacons could have their own propulsion systems, making occasional adjustments to stay properly positioned along evolving routes. Beyond navigation beacons, the next level of infrastructure would be communication relays. While navigation beacons simply broadcast their identity and timing, communication relays would receive, store, and retransmit messages, creating a data network spanning interstellar space. These relays would address one of the fundamental challenges of interstellar travel, the impossibility of real-time communication. A ship traveling to Alpha Centauri cannot have a conversation with Earth. The 4.2-year light speed delay makes this impossible, but delayed communication is better than none. A relay network would ensure that messages eventually reach their destinations, even if years late. Each relay would receive messages from passing spacecraft or from other relays, store them in memory, and retransmit them along the network. A message from a ship near Alpha Centauri bound for Earth would be received by the nearest relay, which would retransmit it to the next relay closer to Earth, which would retransmit it onward, until eventually the message reached the solar system and was delivered to its recipient. The relays would also distribute other information, navigation updates, hazard warnings, traffic advisories, news, entertainment, and anything else that might be useful to travelers or valuable to civilization. They would be the interstellar equivalent of the internet, a network enabling information flow even where physical travel is slow. Building on these basic systems, the next level of infrastructure would be waypoints or rest stations. These would be the interstellar equivalent of truck stops or rest areas on terrestrial highways, places where ships could pause their journey, resupply, make repairs, or simply give crews a break from the monotony of interstellar travel. The design of waypoints would depend on their location. Ideally, they would be positioned near natural resources that could be exploited. A waypoint in orbit around an ice-rich comet could provide water, which can be split into hydrogen and oxygen for fuel and life support. A waypoint in a system with a gas giant could harvest hydrogen or helium for fusion fuel. A waypoint near an asteroid field could provide metals for repairs. Each waypoint would need to be largely self-sufficient, capable of extracting and processing local resources to supply passing ships. It would need fuel storage, repair facilities, possibly habitation for a small maintenance crew, or at least for temporary occupation by ship crews taking shore leave. It would need communication equipment to relay messages and navigation equipment to help ships find it and dock safely. More elaborate waypoints might include manufacturing facilities, capable of producing spare parts or even entire spacecraft components using local resources. The most developed waypoints, positioned in star systems with planets, might grow into full colonies with permanent populations, agriculture, industry, and culture. These would become the cities along the interstellar highway, places where travelers rest, trade occurs, and civilization flourishes. An even more ambitious type of infrastructure would be propulsion assistance systems. Instead of each spacecraft carrying all the energy needed for its journey, external systems could provide acceleration or deceleration, dramatically reducing the fuel each ship must carry. The most developed version of this concept is the laser sail system proposed by projects like Breakthrough Starshot. Enormous laser arrays, potentially based in orbit around the Sun or Moon, would focus gigawatts of laser power onto ultra-thin reflective sails, accelerating lightweight spacecraft to significant fractions of light speed. The spacecraft would carry minimal fuel, with most propulsion provided by external lasers. A more distributed version would position smaller laser stations along routes, each providing incremental boosts to passing spacecraft. A ship might be accelerated by lasers near Earth, receive additional boosts from laser stations positioned along its route, and be decelerated by lasers in the destination system. This would distribute the energy cost across multiple facilities and allow for mid-course corrections and adjustments. Other propulsion assistance systems might use massive electromagnetic launchers, gravitational catapults built around dense objects, or even more exotic systems like pushing against artificially generated fields. The key advantage of all these approaches is that the energy and infrastructure remain stationary while spacecraft move through, rather than each spacecraft carrying its own propulsion system. The most speculative but potentially transformative infrastructure would be permanent faster-than-light systems, if such things prove possible. Wormholes, if they can be created and stabilized, would be fixed installations connecting distant locations. Creating even a single traversable wormhole between our solar system and Alpha Centauri would revolutionize interstellar travel, far more than any number of conventional waypoints. Similarly, if warp drives prove feasible but require enormous infrastructure to function, we might imagine warp gates positioned at key locations, generating the exotic fields needed for faster-than-light travel. Ships would travel conventionally to these gates, pass through while the gate propels them faster than light, then emerge and travel conventionally to their final destination within the target system. The question of how to actually build all this infrastructure is perhaps even more daunting than deciding what to build. The distances and timescales involved make human construction crews impractical for most tasks. We cannot send workers to position a navigation beacon 1 light-year from Earth and expect them to return within their lifetimes. The solution must involve autonomous systems, robots, drones, and artificial intelligence capable of working independently for decades or centuries. Imagine the process of establishing a single waypoint halfway to Alpha Centauri, about 2 light-years from Earth. First, an automated probe would be sent to scout potential locations, perhaps in orbit around a convenient dwarf star or asteroid. This probe would survey local resources, assess the environment, and transmit data back to Earth. 4 years later, when this data arrives, engineers would design the waypoint based on the survey results. Next, construction vessels would be dispatched, perhaps traveling for 50 to 100 years to reach the location. These vessels would need to be entirely autonomous, as communication with Earth would involve 4-year delays each way, making real-time control impossible. The construction AI would need to be sophisticated enough to handle unexpected problems, adapt to unforeseen conditions, and complete a complex construction project over decades with minimal human input. The construction vessels might carry prefabricated components, raw materials, or simply carry the tools to extract and process local resources. Upon arrival, they would begin construction, mining asteroids or comets for materials, manufacturing components using 3D printing or other fabrication techniques, assembling structures, installing equipment, and testing systems. This process might take decades. An AI construction manager would coordinate multiple robots, allocate resources, troubleshoot problems, and gradually bring the waypoint into operation. Only when construction was complete would the waypoint become active, beginning to serve passing spacecraft and relay information back to the rest of the network. Now multiply this process by thousands of facilities across hundreds of light years, and the scale of the challenge becomes apparent. The construction of an interstellar highway network would be a project spanning centuries, requiring the deployment of thousands or millions of autonomous construction systems, consuming resources beyond current human capability to imagine. Advanced artificial intelligence would be absolutely essential. Human engineers could design the overall network and individual components, but the actual construction would need to be delegated to AI systems capable of working independently for timescales far exceeding human lifetimes. These AIs would need to be robust, adaptable, and intelligent enough to handle the unknown challenges of working in environments no human has visited. We might imagine a hierarchy of AI systems. Simple maintenance drones would handle routine repairs and monitoring at completed facilities. More sophisticated construction AIs would build new facilities from plans provided by human engineers. At the highest level, planning AIs might analyze the overall network, identify where new infrastructure is needed, optimize routes, and coordinate the entire construction effort across multiple star systems. This raises profound questions about AI safety and reliability. An AI system deployed to construct a waypoint 2 light-years away will operate beyond human oversight for decades. If it malfunctions, makes poor decisions, or develops unanticipated behaviors, we cannot simply shut it down and fix it. By the time we learn of a problem, years will have passed, and the AI might have caused significant damage or waste. Ensuring AI reliability for such long-term autonomous operation would require advances in AI verification, fail-safe design, and probably some degree of human-level or superhuman intelligence. We would need to be confident that an AI deployed today would still be functioning correctly and pursuing its intended goals a century from now, despite operating in an environment we cannot predict and facing challenges we cannot anticipate. Another approach would be to use self-replicating systems. Instead of sending all the construction equipment and materials from Earth, we might send a small probe carrying the plans and equipment to build copies of itself. Upon reaching its destination, this probe would extract local resources and construct several copies of itself. Some of these copies would remain to build the planned infrastructure, while others would continue onward to the next location, where they would replicate again. This exponential growth would allow a single initial mission to spread throughout the stellar neighborhood, gradually building the infrastructure network without requiring constant launches from Earth. The concept is similar to how life on Earth spread from its origins, with organisms reproducing and colonizing new environments. The risks of self-replicating systems are obvious. If a replicator malfunction or is poorly designed, it might replicate uncontrollably, consuming resources without building useful infrastructure, essentially becoming an interstellar plague. This is the famous Grey Goo scenario, where self-replicating nanomachines consume everything. While nanomachine Grey Goo is probably not a realistic threat due to the limitations of nanotechnology, self-replicating spacecraft could potentially cause problems if not carefully designed with fail-safes and replication limits. The materials needed for interstellar infrastructure would be vast, but, fortunately, space is full of raw materials. The challenge is not availability, but extraction and processing. Every star system contains asteroids rich in metals, comets full of ice and organic compounds, and planets with every element needed for construction. The infrastructure itself could be built almost entirely from local materials, minimizing what must be shipped from Earth. For navigation beacons and communication relays, the primary materials needed would be metals for structure and electronics, silicon for computer chips and solar panels if used, and radioactive isotopes for power if nuclear batteries are employed. All of these can be found in asteroids and processed with automated mining and refining equipment. For larger waypoints with habitation and manufacturing, the material requirements increase but remain feasible. Steel and aluminum for structures, glass or plastics for habitation modules, water and organic compounds for life support, and various metals for machinery and tools, all available from asteroids, comets, and planets. The energy requirements are more challenging. Construction requires energy to mine and process materials, to power manufacturing equipment to assemble structures. In star systems, solar power is available, though it weakens with distance from the star. In deep space between stars, solar power is useless, and nuclear energy would be required. This means that construction of infrastructure in deep space between stars would require either carrying nuclear fuel from nearby star systems or finding it locally, perhaps harvesting it from passing comets or dwarf planets. Alternatively, construction might be powered by beamed energy from star systems, with laser or microwave beams transmitting power across light years to construction sites. Though the inverse square law makes this inefficient over large distances. For the most energy-intensive infrastructure, like laser propulsion stations or warp gates if such things prove possible, the energy requirements would be staggering. A laser array powerful enough to accelerate spacecraft to significant fractions of light speed might require gigawatts or even terawatts of continuous power. This likely means either enormous solar panel arrays in close orbit around a star, or fusion or antimatter power plants. Building such systems would be industrial projects on a scale never before attempted, potentially requiring the resources of entire planets or the capture of significant fractions of a star's output. This sounds absurd by current standards, but civilizations grow in capability over time. The Romans would have found modern construction projects like the Hoover Dam or the Channel Tunnel equally absurd and impossible. The construction of an interstellar highway network would likely follow a pattern of incremental development over centuries. The first phase would establish basic navigation and communication infrastructure along a single route to the nearest star. This might take a century or two, involving the deployment of dozens of beacons and relays across 4 light years. Once this first route is operational, making travel to Alpha Centauri more predictable and safer, the focus would shift to establishing waypoints and refueling stations, turning the route from a bare-bones navigation path into a supported corridor. Meanwhile, new routes would branch out to other nearby stars. Barnard's Star at 6 light-years, Wolf 359 at 7.8 light-years, Lalande 21,185 at 8.3 light-years. Each new route would begin with basic infrastructure and gradually be upgraded. As more routes are established, the network effects would become apparent. A route connecting Earth to Barnard's Star and another connecting Barnard's Star to a third system effectively creates a route from Earth to that third system with Barnard's Star as a waypoint. The network would grow not linearly, but exponentially, each new route multiplying the connectivity of the whole system. By the time this network spans dozens of stars, several centuries from now, it would have transformed from a human project into a self-sustaining system. Resources harvested at waypoints would support their own expansion. AI construction systems deployed decades earlier would have replicated and spread. New star systems being colonized would contribute their own resources and labor to expanding the network. What began as a project requiring immense effort from Earth would become an organic, growing web of infrastructure that maintains and expands itself. Eventually, the distinction between the highway infrastructure and civilization itself would blur. Waypoints would grow into space stations, then colonies, then independent societies. The network would not be something civilization uses, but something civilization is. A distributed network of connected communities spread across the stars, linked by the infrastructure they collectively maintain. The maintenance of this vast infrastructure would itself be a continuous effort. Nothing lasts forever in space. Cosmic rays degrade electronics. Micrometeorites cause impacts. Equipment wears out. Without maintenance, even the most robust beacon would eventually fail. Maintenance would be handled by a combination of built-in redundancy, automated repair systems, and periodic servicing missions. Each piece of infrastructure would be designed to last decades without maintenance, giving time for problems to be detected and repair missions dispatched. Automated repair drones would handle routine maintenance, while more serious problems would require visits from specialized maintenance vessels, or even human engineers. For the most complex systems, the communication network would allow infrastructure to report its status continuously. A navigation beacon beginning to malfunction could transmit a distress signal, alerting maintenance systems that intervention is needed. Given the light speed delays involved, this would not allow for immediate response, but it would ensure that problems are eventually addressed before they cascade into failures. Over centuries, parts of the infrastructure would need to be replaced entirely as technology advances. A navigation beacon designed with century-old technology would eventually be obsolete, replaced by newer, more capable systems. This process of renewal would be continuous, the network constantly updating itself the way terrestrial infrastructure is periodically rebuilt and modernized. The cost of building an interstellar highway network would be, in some sense, immeasurable. How do you calculate the cost of a project spanning centuries and involving resources from multiple star systems? But perhaps cost is the wrong framework. Infrastructure is not an expense but an investment. The Roman roads cost enormous resources to build, but generated vastly more value through the trade, military efficiency, and cultural integration they enabled. Similarly, an interstellar highway network would be built not as an expense but as an investment in humanity's future. Each waypoint constructed, each route established, would make interstellar travel easier and cheaper, enabling commerce, exploration, and cultural exchange that would repay the investment many times over. The network would make possible things that are impossible without it. Rapid colonization of new worlds, interstellar trade in exotic resources, cultural unity across light years, and the resilience that comes from spreading across many systems. From our current perspective, looking at the immense challenges and the centuries of effort required, building an interstellar highway might seem like an impossible dream. But consider how much human capability has grown in just the past few centuries. 500 years ago, crossing the Atlantic Ocean was a perilous expedition taking months. Today, it is a 6-hour flight. 500 years from now, with technologies we can barely imagine and resources drawn from across the solar system, building infrastructure across light years might seem no more impossible than building a transcontinental railroad seemed to 19th century Americans. Challenging, requiring dedication and resources, but ultimately achievable. The key is to begin. The first navigation beacon positioned in deep space. The first autonomous construction probe sent toward another star. The first successful test of technology that will eventually form part of the network. Each of these steps, individually modest, would be part of a progression leading toward a future where the stars are not isolated points of light, but connected nodes in a vast network, joined by highways invisible but real, built by the patient effort of generations, maintained by artificial minds, and traveled by the descendants of those who first dreamed of roads between the stars. In 1804, the Lewis and Clark expedition set out from St. Louis to explore the western territories of North America and find a route to the Pacific Ocean. Their propulsion system was simple: human muscle power, augmented occasionally by horses and the current of rivers. They walked, they rowed, they portaged their boats around rapids. The journey to the Pacific and back took 2 years and 4 months, covering roughly 8,000 miles. It was grueling, dangerous, and pushed the limits of human endurance. Today, you can fly from St. Louis to the Pacific coast in about 4 hours. The difference is not the distance, which remains the same, but the propulsion system. Modern jet engines, burning refined kerosene and compressing air at high velocities, can move hundreds of passengers across a continent in less time than it takes to watch 2 movies. The evolution of propulsion technology transformed an epic expedition into a routine trip. For interstellar travel to become routine, we need a similar revolution in propulsion. The chemical rockets that have served us well for travel within our solar system are hopelessly inadequate for crossing the light years between stars. To build a true interstellar highway system, We need propulsion technologies that can accelerate spacecraft to significant fractions of light speed, sustain them during journeys lasting years or decades, and do so with reasonable energy efficiency and cost. The fundamental challenge of any propulsion system is expressed in Newton's third law. For every action, there is an equal and opposite reaction. To move forward, you must push something backward. Rockets work by expelling mass at high velocity. The reaction to this expelled mass pushes the rocket in the opposite direction. The faster you expel the mass and the more mass you expel, the more momentum you gain. This leads to the rocket equation, the mathematical relationship discovered by Konstantin Tsiolkovsky that describes how much velocity change a rocket can achieve based on its mass ratio and exhaust velocity. The equation tells us something profound and discouraging. To go faster, you need more fuel, but more fuel means more mass, which means you need even more fuel to accelerate that mass, leading to exponentially growing fuel requirements. Chemical rockets expel their exhaust at a few kilometers per second, which is enough for Earth orbit or trips to Mars, but nowhere near enough for interstellar travel. To achieve the velocities needed to cross light years in reasonable timeframes, we need propulsion systems with much higher exhaust velocities, ideally approaching the speed of light itself. Nuclear propulsion offers the first major improvement over chemical rockets. Nuclear reactions release millions of times more energy per unit mass than chemical reactions, providing the potential for much higher exhaust velocities. The simplest form of nuclear propulsion is nuclear thermal propulsion, where a nuclear reactor heats hydrogen or another propellant to extreme temperatures before expelling it through a nozzle. This can achieve exhaust velocities of 8 to 10 kilometers per second, roughly twice that of chemical rockets. While better than chemical propulsion, nuclear thermal systems are still inadequate for interstellar travel. They provide incremental improvement, not the revolutionary change needed. To truly harness nuclear energy for interstellar propulsion, we need more radical approaches. Nuclear pulse propulsion, studied seriously in the 1950s and 60s under Project Orion, involves detonating nuclear bombs behind a spacecraft and riding the blast wave. This sounds insane, but the physics is sound. Each explosion pushes against a massive shock absorber plate, accelerating the ship forward. By detonating thousands of bombs in succession, the ship builds up tremendous velocity. Project Orion calculations suggested that such a system could achieve 5 to 10% of light speed, reducing the journey to Alpha Centauri to 40 to 80 years. The ship would need to be massive to survive the repeated nuclear explosions, with the shock absorber plate weighing hundreds of tons. But the specific impulse, a measure of propulsion efficiency, would be orders of magnitude better than chemical rockets. The problems with nuclear pulse propulsion are primarily political and environmental rather than technical. Detonating thousands of nuclear weapons, even in space, raises obvious concerns about nuclear proliferation, radiation, and the weaponization of space. The Partial Test Ban Treaty of 1963 effectively ended Project Orion by banning nuclear explosions in space. Whether future civilizations would revive this concept depends on whether these concerns can be addressed or whether alternative technologies prove superior. A more elegant nuclear approach is fusion propulsion. Fusion reactions, which power the sun and other stars, combine light elements like hydrogen isotopes into heavier elements, releasing enormous energy in the process. Unlike fission reactions, which split heavy atoms, fusion uses abundant light elements and produces far less radioactive waste. Fusion propulsion has been studied in various forms. The simplest concept is similar to nuclear pulse propulsion, but using fusion bombs instead of fission bombs. More sophisticated designs involve continuous fusion reactions in a magnetic confinement chamber, with the fusion products directed out a magnetic nozzle to provide thrust. The challenge is that we have not yet achieved practical fusion power even for stationary applications on Earth, let alone for spacecraft. Fusion requires heating hydrogen isotopes to temperatures of millions of degrees and confining them long enough for fusion to occur. The energy input required to achieve these conditions has, so far, exceeded the energy output from fusion, making the process net negative in energy terms. However, progress continues. In December 2022, scientists at the National Ignition Facility achieved fusion ignition for the first time, producing more energy from fusion than was delivered to the fuel. While this was in a laboratory setting using a different approach than would be practical for propulsion, it demonstrated that the physics of net positive fusion is sound. If practical fusion propulsion can be developed, it would be transformative for interstellar travel. Fusion fuel, likely deuterium and helium-3, could be harvested from gas giants or from the solar wind. A fusion rocket could potentially achieve exhaust velocities of 10% of light speed, allowing spacecraft velocities of 10 to 20% of light speed with reasonable mass ratios. This would reduce travel time to Alpha Centauri to 20 to 40 years, making interstellar journeys possible within a human lifetime. For even higher performance, we turn to antimatter propulsion. Antimatter is exotic matter composed of antiparticles, positrons instead of electrons, antiprotons instead of protons. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's equation E equals mc squared. This is the most efficient energy release possible under known physics. A single kilogram of antimatter annihilating with a kilogram of matter would release energy equivalent to 43 megatons of TNT, roughly equal to the largest nuclear weapon ever detonated. The specific impulse of an antimatter rocket would be limited only by how effectively you can direct the annihilation energy into thrust, potentially achieving exhaust velocities of 30 to 50% of light speed. With antimatter propulsion, spacecraft could potentially reach 50 to 70% of light speed, reducing the journey to Alpha Centauri to just 6 to 8 years. This would make interstellar travel practical on timescales similar to lengthy terrestrial expeditions of previous centuries. A person could depart Earth as a young adult, reach another star system in middle age, and potentially return to Earth before the end of their natural lifespan, though they would have aged far less than those who remained behind due to relativistic time dilation. The problem with antimatter propulsion is not physics, but engineering and economics. Producing antimatter is extraordinarily difficult and expensive. Current production rates at CERN and Fermilab measure in nanograms per year, and the energy input required to create antimatter vastly exceeds the energy you get back when it annihilates. The cost of antimatter production is estimated at trillions of dollars per gram. Even if production could be scaled up dramatically, storing antimatter presents severe challenges. Antimatter cannot touch normal matter without annihilating, so it must be contained in electromagnetic traps, suspended in vacuum by magnetic fields. Any failure of the containment system would result in immediate catastrophic annihilation. For a spacecraft carrying kilograms of antimatter, the storage system must be utterly reliable for the years or decades of an interstellar journey. Despite these challenges, antimatter propulsion remains a serious candidate for future interstellar travel. The advantages are so compelling that significant research continues into antimatter production, storage, and propulsion system design. If production costs can be reduced by several orders of magnitude, perhaps through more efficient production methods or by harvesting antimatter from natural sources like radiation belts or cosmic ray interactions, antimatter propulsion could become practical. While nuclear and antimatter propulsion rely on carrying fuel, another approach is to leave the propulsion system behind and push the spacecraft from a distance. This is the principle behind laser sail propulsion, also called beam propulsion or light sail technology. A laser sail spacecraft consists of an ultra-thin, ultra-lightweight reflective sail, typically made of materials like aluminum or graphene just a few atoms thick, attached to a minimal payload. Enormous laser arrays, positioned in Earth orbit or on the Moon, focus gigawatts of laser power onto the sail. Photons from the laser bounce off the sail, transferring momentum and accelerating the spacecraft. Because the spacecraft carries no fuel, only the sail and payload, its mass can be extremely low. A probe weighing just a few grams with a sail a few meters across could potentially be accelerated to 20% of light speed by sufficiently powerful lasers, reaching Alpha Centauri in about 20 years. This is the concept behind Breakthrough Starshot. Announced in 2016 with backing from physicist Stephen Hawking and investor Yuri Milner. The project aims to develop the technology to send small probes to Alpha Centauri within a generation. The challenges are immense. The laser array would need to produce roughly 100 gigawatts of power. The sail must be incredibly thin, yet strong enough to withstand intense laser heating, and the targeting must be extraordinarily precise to keep the laser focused. On a sail that will eventually be trillions of miles, away laser sail propulsion has significant advantages for an interstellar highway system. Once the laser infrastructure is built, it can be reused to launch many spacecraft with minimal additional cost. The spacecraft themselves are cheap because they carry no fuel or propulsion system, and because they can reach high velocities, travel times are reduced to decades rather than centuries. However, laser sails also have severe limitations. They work well for small, fast probes but scale poorly to larger crewed vessels. The sail size increases with payload mass, and laser power requirements increase even faster. A crewed ship, weighing thousands of tons, would require impossibly large sails and laser arrays, far beyond anything contemplated even in speculative designs. More problematically, laser sails provide no way to slow down. A probe accelerated to 20% of light speed by lasers from Earth will zip through the Alpha Centauri system at that same speed, with only hours to conduct observations before continuing into deep space. For the probe to stop and enter orbit around the destination, STAR requires either carrying fuel for deceleration, which defeats much of the mass advantage, or having a second laser array at the destination to decelerate the probe, which requires establishing infrastructure there first. One solution is magnetic sails or magsails, which use magnetic fields to push against the interstellar medium or the destination star's stellar wind. A spacecraft could be accelerated by laser sails, then deploy a large magnetic field as it approaches its destination, using the interaction with charged particles in the stellar wind to gradually brake. This combines the advantages of laser sail acceleration with the ability to decelerate without carrying fuel. Another approach entirely abandons carrying propellant and instead harvests it from space itself. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, would use enormous electromagnetic fields to scoop up hydrogen atoms from the interstellar medium. This hydrogen would be funneled into a fusion reactor, and the fusion products expelled as exhaust. The genius of this concept is that the spacecraft never runs out of fuel. It continuously harvests new fuel as it travels. If such a system could work, it would enable arbitrarily long voyages at high speeds, limited only by the lifespan of the spacecraft and crew rather than fuel capacity. The ramjet could continuously accelerate, potentially reaching velocities approaching the speed of light over time. Unfortunately, the physics of the Bussard ramjet presents severe problems. The interstellar medium is far less dense than Bussard originally assumed, containing only about 1 hydrogen atom per cubic centimeter on average. To collect sufficient fuel, the ramjet's magnetic scoop would need to be hundreds or thousands of kilometers in diameter, far larger than any structure we could conceivably build. Moreover, the drag from scooping up this hydrogen might exceed the thrust gained from fusing it. meaning the ramjet might actually slow down rather than accelerate. Various modifications to the basic ramjet concept have been proposed to address these issues, but none have proven entirely convincing. The ramjet remains an elegant idea that likely will not work in practice, at least not with our current understanding of physics and engineering. For an interstellar highway system, the optimal propulsion strategy would likely be hybrid, using different systems for different phases of the journey and different types of missions. Fast, lightweight probes might use laser sails, accelerated to high velocities for quick reconnaissance or to carry messages. Cargo vessels carrying bulk materials might use slower but more fuel-efficient fusion or nuclear pulse systems, taking decades or centuries, but moving enormous masses. Crewed ships would use whatever provides the best balance of speed, safety, and life support duration, probably fusion or possibly antimatter if it becomes practical. Critical to any of these propulsion systems is the question of energy sources. Accelerating even a small spacecraft to relativistic velocities requires staggering amounts of energy. Where does this energy come from, and how is it stored, generated, or transferred? For laser sail systems, the energy comes from ground-based or space-based laser arrays. These would be enormous installations, potentially requiring their own dedicated power plants. A 100 gigawatt laser array would require power equivalent to roughly 100 large nuclear power plants operating continuously. This energy might come from solar arrays in orbit close to the sun where sunlight is intense, from fusion power plants if that technology matures, or from other advanced power sources. For ships carrying their own fuel, the energy is stored in the fuel itself, whether chemical, nuclear, or antimatter. The challenge is energy density. How much energy can be stored per unit mass? Chemical fuels have low energy density. Nuclear fuels are vastly better. Antimatter has the maximum possible energy density, converting 100% of mass to energy. For long journeys, spacecraft might need to refuel along the way, making energy transfer and refueling stations a critical part of interstellar highway infrastructure. How would such stations work across interstellar distances? The simplest approach is to position refueling stations at waypoints along established routes, as discussed in the previous section on infrastructure. A ship traveling from Earth to a star 40 light-years away might stop at waypoints every 8 to 10 light-years to refuel, breaking the journey into manageable segments. These refueling stations would need to produce or store fuel locally. For fusion propulsion, the station would need to harvest fusion fuel from local sources. The ideal location would be in orbit around a gas giant where deuterium could be extracted from the atmosphere. Helium-3, another potential fusion fuel, is rare on Earth, but more common in gas giants, and might be harvested from the solar wind or the lunar surface in our solar system. For antimatter propulsion, refueling becomes more complex. Antimatter cannot be harvested naturally in significant quantities. It must be produced. This likely means positioning antimatter production facilities in high-power locations, possibly in close orbit around stars where enormous solar arrays can capture stellar energy, or around fusion power plants. The antimatter would then be stored at refueling stations for use by passing ships. An intriguing alternative is beamed energy transfer. Instead of physically refueling ships, energy could be transmitted across space using lasers or microwaves. A ship with depleted fuel reserves could receive beamed energy from a nearby station, or even from distant stellar systems, using this energy to power electric propulsion systems or to synthesize new fuel. The efficiency of beamed energy decreases with the square of distance due to beam spreading, making it practical only over relatively short ranges, perhaps a few light months at most. But within this range, it could provide a way to assist ships without requiring them to physically dock at stations, reducing travel time and increasing flexibility. This leads to the question of whether an interstellar highway system would require a universal energy grid analogous to electrical power grids on Earth. The concept is appealing. A network of power generation facilities, transmission systems, and distribution points ensuring that energy is available wherever needed throughout the highway system. Such a grid would offer several advantages. Energy could be generated where it is most efficient, such as in close orbit around stars, and transmitted to where it is needed. Ships would not need to carry as much fuel if they could draw power from the grid at regular intervals. The grid would also power other infrastructure: navigation beacons, communication relays, habitats, and manufacturing facilities. However, the physics of interstellar distances makes a true universal grid extremely challenging. Transmitting power across light years with lasers or microwaves is hopelessly inefficient due to beam spreading. Even at shorter distances measured in light months, transmission losses would be enormous. A more realistic approach would be a series of local power grids, each spanning a single star system or a region of a few light months. Each grid would be self-contained, generating its own power and distributing it locally. Long-distance energy transfer between systems would occur not through beamed power, but through physical transport of energy-dense fuels, fusion fuel shipments, antimatter in magnetic bottles, or even mass itself, if we consider matter as a form of stored energy per Einstein's equation. These local grids would resemble the regional power grids on Earth, which are interconnected for redundancy and load balancing, but operate somewhat independently. The interstellar highway would tie together multiple independent energy grids rather than forming a single unified grid. Within each grid, different energy sources might be used depending on local conditions. Star systems with abundant planets would favor fusion power, harvesting deuterium and helium-3 from gas giants. Systems with particularly bright or massive stars might use enormous solar collectors in close orbit. Systems with access to antimatter production might specialize in this, becoming the fuel suppliers for the broader highway network. The development of propulsion and energy systems would follow a progression similar to other technologies. Early interstellar missions would use whatever technology is available, probably nuclear pulse or early fusion systems, accepting journey times measured in centuries. As technology advances, ships would become faster and more efficient, and infrastructure would be built to support them. The first refueling stations would be simple: stockpiles of fuel gathered from local resources, tended by automated systems, providing basic services. Over time, these would grow into complex facilities with manufacturing, repair capabilities, and eventually permanent populations. The energy infrastructure would expand in parallel, from basic solar panels and nuclear reactors to sophisticated fusion plants and potentially antimatter production. Each generation of propulsion technology would extend the reach and reduce the travel time of the highway network. The first routes might take centuries to traverse with nuclear pulse propulsion. Fusion propulsion might reduce this to decades. If antimatter propulsion becomes practical, travel times drop to years. And if some breakthrough physics enables faster-than-light travel through warp drives or wormholes, the nature of the highway changes entirely, from a system managing multi-decade journeys to one coordinating rapid transits between distant stars. The propulsion systems used by different ships might vary widely, just as terrestrial highways accommodate everything from motorcycles to 18-wheel trucks, each with different engines, fuel requirements, and performance characteristics. The highway infrastructure would need to support this diversity, providing different types of fuel, different power coupling standards, and different services for different ship types. There might even be specialized lanes or routes optimized for particular propulsion types. A laser sail route would have powerful laser arrays at the origin and destination, but require minimal infrastructure along the way. A fusion propulsion route would have refueling stations positioned at intervals where gas giants can be harvested. An antimatter route would connect systems with antimatter production capabilities, with heavily shielded storage facilities at waypoints. The economic implications of different propulsion systems are profound. The cost per kilogram to transport cargo between stars depends primarily on energy costs and travel time. Fast propulsion systems like antimatter or laser sails have high energy costs but short travel times. Slow systems like early fusion or nuclear pulse propulsion have lower energy costs but much longer travel times, which translates to capital costs as ships and their cargoes are tied up for decades or centuries. The optimal choice depends on what is being transported and how urgently it is needed. Time-sensitive cargo, perishable goods or passengers would pay premium prices for fast transport. Bulk raw materials, non-perishable goods, or data that can be transmitted at light speed might use slower, cheaper transport. This would lead to market segmentation, with different propulsion systems serving different economic niches, much as we see in terrestrial freight transport where air cargo, trucking, rail, and maritime shipping each serve different markets based on speed, cost, and cargo type. Ultimately, the propulsion and energy systems of an interstellar highway are not just technical challenges, but economic and strategic questions. The civilization that controls key energy production facilities or fuel sources would have significant power over interstellar commerce. The development of more efficient propulsion systems would provide competitive advantages to their operators, and the overall architecture of the highway system would reflect the propulsion technologies available, changing and adapting as new technologies emerge. Looking forward from our current position, with chemical rockets and early ion drives as our most advanced operational systems, the propulsion requirements for a true interstellar highway seem daunting, perhaps impossible. But consider what would have seemed impossible to people just a few centuries ago: flying across oceans in hours, generating electricity from splitting atoms, sending humans to the moon. Each generation's impossibilities become the next generation's routine technologies. The propulsion systems that will power the interstellar highway likely cannot be built today, but they can be imagined, studied, and gradually developed. Nuclear pulse propulsion is technically feasible right now if we chose to pursue it. Fusion propulsion awaits the achievement of practical fusion power on Earth, which seems increasingly likely in the coming decades. Laser cell technology is being actively tested with projects like Breakthrough Starshot. Even antimatter propulsion, while far beyond current capabilities, is not forbidden by physics, only by economics and engineering. Each step forward in propulsion technology, each incremental improvement in energy generation and storage, each new insight into the physics of space-time and matter brings the interstellar highway closer to reality. The engines that will power ships between the stars may not yet exist, but the principles that will govern them are already known, waiting to be refined, developed, and deployed by future generations who look at the stars not as distant, unreachable lights but as destinations connected by highways, ready to be traveled. In 1858, workers completed the first transatlantic telegraph cable, stretching nearly 2,000 miles along the ocean floor between Ireland and Newfoundland. For the first time in human history, messages could cross the Atlantic in minutes, rather than the weeks required for ships to carry letters. Queen Victoria sent a congratulatory message to President Buchanan that took 16 hours to transmit, 98 words traveling slowly through the copper wire. Despite its technical problems and brief lifespan before failure, this cable represented a revolution in human connectivity. Today, fiber optic cables crisscross the ocean floors, carrying billions of messages instantaneously between continents. A person in London can have a video conversation with someone in New York with barely perceptible delay. The world has become, in terms of communication, effectively small. Distance no longer imposes meaningful barriers to real-time interaction. But interstellar space presents a challenge that no technology can overcome through simple engineering improvements: the absolute speed limit of light. No signal, no message, no information of any kind can travel faster than light through normal space. This is not an engineering limitation, but a fundamental feature of the universe itself. embedded in the structure of space-time. Light travels at approximately 300 million meters per second, which sounds extraordinarily fast until you consider interstellar distances. A light signal from Earth to the Moon takes 1.3 seconds. To Mars, depending on orbital positions, it takes between 3 and 22 minutes. To Pluto at its most distant, over 5 hours. These delays are manageable, if inconvenient. But to Alpha Centauri, our nearest stellar neighbor at 4.24 light-years, a signal takes 4.24 years to arrive. Send a message today, and you will not receive a response for 8.5 years at minimum, assuming the recipient replies immediately. For more distant stars, the delays multiply proportionally. A star 50 light-years away imposes a 100-year round-trip communication delay. This fundamental constraint shapes every aspect of how an interstellar highway system would function. Unlike terrestrial highway systems, where traffic control can coordinate vehicles in real time and central authorities can respond immediately to problems, an interstellar highway must operate without the possibility of real-time coordination. Each spacecraft, each waypoint, each piece of infrastructure must be capable of autonomous operation because help from home, if it comes at all, will arrive years too late. The simplest and most reliable method of interstellar communication is also the oldest. Radio waves. Radio is just another form of light, at longer wavelengths than visible light but traveling at the same speed. Radio waves can carry information efficiently, can be generated and detected with relatively simple equipment, and penetrate dust and gas that would block visible light. For over a century, humans have been broadcasting radio signals, both intentionally and as leakage from our communications and radar systems. These signals have spread outward in an expanding sphere, currently about 100 light-years in radius, carrying inadvertent news of our existence to any civilizations that might be listening. Similarly, we have been listening for radio signals from other civilizations through projects like SETI, the search for extraterrestrial intelligence. For an interstellar highway system, radio communication would form the backbone of the network. Much as undersea cables form the backbone of Earth's internet, spacecraft would carry powerful radio transmitters and sensitive receivers. Waypoints would include communication relays that receive, store, and retransmit messages. The network would propagate information across the stellar neighborhood, each relay passing messages along until they reach their destinations. A message sent from a ship near Alpha Centauri bound for Earth would be transmitted to the nearest relay station, perhaps positioned 1 light-year closer to Earth. This relay would receive the message, store it, and retransmit it to the next relay, which might be another light-year closer. The message would hop from relay to relay, each transmission covering a light-year, until finally reaching Earth's orbital relays and being delivered to its recipient. The total transmission time would still be limited by the speed of light. No relay system can make messages travel faster than light itself, but relays provide reliability, amplification, and routing. Without relays, a signal from Alpha Centauri would weaken according to the inverse square law, spreading out as it travels until it might be too faint to detect above background noise. Relays receive the weakened signal, amplify it, and retransmit at full strength, ensuring the message reaches its destination. Relays also provide redundancy. If one relay fails, messages can be rerouted through other relays. This is similar to how the internet was designed to be resilient, with packets finding alternative routes if parts of the network fail. For an interstellar network spanning light-years, where repair missions might take decades to reach a failed relay, this redundancy is essential. The positioning of relays would follow the major routes of the highway system. A route from Earth to Alpha Centauri might have relays every half light-year or so, requiring 8 or 9 relays for the complete route. As the network expands to cover more stars, the relay network would grow proportionally, eventually forming a dense web, ensuring that any location within the network has multiple paths for message routing. Beyond radio, optical communication using lasers offers certain advantages. Lasers can carry more information than radio for a given power level, and because laser beams are much narrower than radio signals, they spread less over distance, remaining detectable over larger ranges. A sufficiently powerful laser communication system might require fewer relays than radio, reducing infrastructure costs. The James Webb Space Telescope, operating near Earth, uses laser communication to transmit data at rates up to 28 megabits per second from nearly 1 million miles away. Scaling this technology to interstellar distances would require more powerful lasers and more sensitive detectors, but the physics is straightforward. However, laser communication has significant drawbacks. The narrow beam must be aimed precisely at the receiver, which becomes increasingly difficult over light years. A tiny error in aiming angle, imperceptible over short distances, results in the beam missing its target by billions of miles over interstellar distances. Any dust or gas between transmitter and receiver can scatter or absorb the laser light, potentially blocking the signal entirely. Radio waves, with their longer wavelengths, are more resistant to such interference. The optimal solution would likely be a hybrid system using both radio and laser communication. Radio would provide reliable, always available communication with wide coverage, ensuring that any ship or facility can always send and receive messages. Laser communication would supplement this with high bandwidth channels for data-intensive transmissions like scientific data, entertainment media, or detailed technical information. The protocols for interstellar communication would necessarily differ from terrestrial internet protocols, which assume rapid message delivery and the possibility of real-time interaction. With years of transmission delay, requesting retransmission of lost packets would be impractical. Instead, interstellar communication would likely use forward error correction, embedding redundant information in the message itself, so that the receiver can reconstruct the original even if parts are lost or corrupted. Messages would also need to be self-contained rather than interactive. Instead of the back and forth of terrestrial conversations, interstellar communication would resemble letters or recorded messages, with each transmission containing complete thoughts or information packages, designed to be understood without immediate response. The delay would profoundly affect how interstellar civilization functions. Consider a colony orbiting Tau Ceti, 12 light-years from Earth. News from Earth is always 12 years old by the time it arrives. Any request for help, advice, or information requires a 24-year round trip before a response arrives. A child born in the colony would be approaching adulthood before learning Earth's reply to questions asked at their birth. This enforces a level of autonomy unknown in our interconnected modern world. The Tau Ceti colony cannot rely on Earth for real-time decision-making, technical support, or emergency assistance. It must be self-sufficient, capable of handling any crisis with local resources and knowledge. The communication link to Earth provides cultural connection, technical information, and long-term coordination, but cannot provide real-time support. This would likely lead to a particular pattern of communication. Regular scheduled transmissions would carry bulk data, news, entertainment, scientific papers, technical documentation, cultural works, personal letters, and any other information worth sending. Each transmission might contain terabytes of data, compressed and encoded for reliability, representing everything produced since the last transmission. Emergency messages would be given priority routing, but would still face the same light speed delays. A distress call from a damaged ship near a waypoint would reach the nearest relay in months or years, depending on distance, and the reply would take equally long to return. Help, if it comes, would come from other nearby ships or facilities, not from distant Earth. This brings us to one of the most tantalizing questions in physics. Could quantum entanglement enable faster-than-light communication bypassing the light speed barrier and allowing real-time contact across interstellar distances. Quantum entanglement is a genuine phenomenon in which two particles become correlated, such that measuring one particle instantly affects the state of the other, regardless of the distance between them. Einstein famously called this spooky action at a distance because it seemed to violate the principle that no influence can travel faster than light. Entanglement has been experimentally verified countless times and is now well understood within quantum mechanics. If you entangle two particles and separate them by any distance, even light years, measuring one particle in a certain way will instantaneously determine the state of the other particle. This sounds like it should enable faster than light communication. Take two entangled particles, keep one on Earth and send the other to Alpha Centauri. When you want to send a message, measure your particle in a way that encodes the message, and the instant correlation should transmit the information to Alpha Centauri faster than light. Unfortunately, this does not work. The subtle reason involves the nature of quantum measurement and information. When you measure your entangled particle, you get a random result. The particle might be spin up or spin down with 50-50 probability. Your measurement does indeed instantly affect the distant particle, which will now definitely be found in the opposite state if measured the same way. But the person at Alpha Centauri measuring their particle also gets a random result, only by comparing the two sets of measurements. Using conventional slower-than-light communication, can you verify that the particles were entangled and correlated? The entanglement is there, the correlation is real, but it cannot be used to transmit information faster than light, because neither party can control what result they get, and neither can see the correlation without comparing notes through conventional means. This has been proven rigorously in physics through no-communication theorems, which demonstrate that quantum mechanics, as currently understood, cannot be exploited for faster-than-light communication. Any apparent method of using entanglement for signaling turns out, upon closer analysis, to require conventional communication to verify or interpret the results. This is deeply disappointing for interstellar highway systems because real-time communication would solve so many problems. Ships could call for help and receive immediate assistance. Traffic could be coordinated centrally. Cultural and emotional connections between distant colonies would be maintained far more easily. The entire character of interstellar civilization would be different with real-time communication. However, we must be cautious about declaring anything absolutely impossible. Our understanding of quantum mechanics, while extremely successful and thoroughly tested, may not be complete. There could be undiscovered physics that allows faster-than-light communication through some mechanism we do not yet understand. Some speculative theories in physics do suggest possible loopholes. If wormholes exist and can be stabilized, they might allow communication through the wormhole, with signals traveling shorter distances through higher dimensional space. The signal still travels at light speed through the wormhole. But if the wormhole provides a shortcut through space-time, the effective communication speed could appear faster than light from the perspective of normal space. Similarly, if some form of faster-than-light travel proves possible through warp drives or other exotic means, these same mechanisms might enable faster-than-light communication. A warp bubble that moves space rather than moving through space might carry communication signals along with spacecraft, enabling messages to traverse light years in days or weeks rather than years. But these remain speculative. Based on our current, well-tested understanding of physics, faster-than-light communication appears impossible, and any interstellar highway system must be designed to function without it. Given this constraint, how would navigation, updates, and coordination work across star systems? The answer is through careful planning, autonomous systems, and acceptance of delayed information. Navigation would rely primarily on autonomous systems aboard each spacecraft. As discussed in the earlier section on mapping routes, ships would use pulsar navigation or stellar position measurements to determine their location, compare this to their planned route, and make corrections as needed. This requires no communication with other systems and works regardless of isolation. However, navigation updates from the broader network would still be valuable. New hazards might be discovered: a dense dust cloud that was not previously mapped, a rogue planet drifting through a route, or increased radiation from a stellar flare. As ships encounter and report these hazards, the information propagates through the communication network, eventually reaching all ships and facilities. A ship departing Earth for Alpha Centauri would download the latest navigation data before departure, including all known hazards, updated stellar positions accounting for proper motion, and optimal route parameters. During the journey, it would continue receiving updates via the relay network. A new hazard discovered 3 light-years along the route would be reported by the discovering ship, transmitted back through relays, processed by route planning systems, and broadcast to all ships on that route. By the time our ship traveling to Alpha Centauri reaches the 3 light-year point, if the hazard was discovered more than 3 years ago, it will have received the warning in time to alter course. If the hazard was discovered more recently, the ship might encounter it before the warning arrives, but would itself report it, contributing to the collective knowledge. This creates a system of distributed, asynchronous information sharing. No central authority has real-time knowledge of all ships and conditions, but information eventually propagates to where it is needed, and the system as a whole becomes more knowledgeable over time. Coordination of traffic would work similarly. In terrestrial air traffic control, controllers manage thousands of aircraft simultaneously, constantly updating flight paths to maintain safe separation and optimize flow through congested airspace. This requires real-time communication and coordination. Interstellar traffic coordination cannot work this way. Instead, it would rely on established procedures and rules that ships follow autonomously, similar to maritime navigation rules that allow ships to safely navigate without constant coordination with shore authorities. Ships would be assigned routing lanes and schedules before departure. A ship leaving Earth for Alpha Centauri might be assigned to depart during a specific launch window, follow a particular trajectory, and maintain a certain velocity profile. These assignments would ensure adequate separation from other ships without requiring real-time coordination. As ships travel, they would broadcast their position and status periodically. These broadcasts would propagate through the network, allowing other ships and facilities to build a picture of where traffic is located. Because the information is delayed by light speed, it is always outdated, but for ships traveling at small fractions of light speed, even year-old position information is useful for long-term planning. Emergency coordination would rely on nearby ships and facilities rather than distant central authorities. If a ship suffers a critical failure and needs assistance, it broadcasts a distress signal. The nearest ships and waypoints, typically within a few light months, receive this signal within weeks or months and can respond. Meanwhile, the distress signal propagates through the network, informing the broader system, but immediate assistance comes from those nearby. This is similar to maritime distress calls, where nearby ships are expected to render assistance, while distant authorities are informed but cannot immediately help. The vastness of ocean distances is nothing compared to interstellar distances, but the principle is the same. Help comes from those close enough to reach you in reasonable time. System-wide updates and policy changes would be distributed through the communication network and implemented on long timescales. If traffic rules need to be changed, new hazard categories defined, or new procedures implemented, these updates would be broadcast throughout the network with implementation dates scheduled years or decades in the future, ensuring all parties receive the information before it takes effect. For example, if a new high-speed corridor is established requiring special procedures, this information might be broadcast 10 years before the corridor opens, ensuring even ships in the most distant reaches of the network receive the update before anyone attempts to use the new corridor. cultural and personal communication would face the same light-speed barriers. A person living in a colony at Tau Ceti could exchange letters with family on Earth, but each exchange would take 24 years. A question sent from the colony as a child would receive an answer when that child is approaching middle age. Conversations would span generations, with grandparents on Earth writing letters that their grandchildren on Tau Ceti would eventually read. This would create a unique form of communication, different from both historical letters, which at least arrived within the sender's lifetime, and modern instant messaging. It would be more like messages in bottles, cast into the temporal ocean, hoping to reach someone who remembers the context and cares about the contents. Some colonists might maintain one-sided journals, recording their lives and thoughts, and periodically transmitting them to Earth, not for response, but simply to maintain a record. A cultural connection across the light years. Earth might broadcast entertainment, news, scientific discoveries, and cultural works to all colonies, not expecting responses, but providing connection to humanity's origin world. The psychological and social implications are profound. Humans have never before lived in such enforced isolation while maintaining awareness of a broader civilization. A colony at Tau Ceti knows Earth exists, receives its news and culture, but cannot interact with it in any meaningful real-time way. This could lead to feelings of isolation and alienation, or it could foster strong local community and independence. Different colonies would likely diverge culturally over time, their societies shaped by local conditions and the decades-long communication delays that prevent real-time cultural exchange. Tau Ceti colony might develop its own language variations, customs, and social structures. When news finally arrives from Earth, it describes a world that has changed dramatically since the colony last sent information. Yet the communication links, however delayed, would prevent complete isolation. The colonies would remain aware they are part of something larger, part of an interstellar civilization connected by invisible threads of radio signals and laser light, carrying information across the void at the maximum speed the universe allows. The infrastructure to support this communication network would itself be substantial. Each relay station needs a powerful transmitter capable of reaching the next relay, typically a light year or more away. It needs a sensitive receiver capable of detecting weak signals from ships passing through its region. It needs data storage to buffer messages while waiting for the next transmission window. It needs enough intelligence to route messages appropriately, compress and decompress data, handle errors, and maintain itself. The protocols would need to be extremely robust. A message might pass through dozens of relays over decades, and losing it to a single relay failure would be unacceptable. This suggests heavy redundancy, messages transmitted along multiple paths simultaneously, with error correction allowing reconstruction, even if some copies are lost or corrupted. The network would also need security. In the early days of an interstellar highway, with only a few colonies and routes, trust might be assumed. But as the network grows to include hundreds of colonies and thousands of ships from different organizations, cultures, and potentially different species, if we encounter alien civilizations, security becomes critical. Messages would likely be encrypted end-to-end, unreadable by the relays that carry them. Digital signatures would verify message authenticity. Protocols would prevent spoofing, where someone pretends to be another sender. The network would need to resist both deliberate attacks and accidental interference. The bandwidth of the interstellar communication network would be limited but probably adequate for most purposes. Radio and laser communication can carry substantial data rates, potentially gigabits per second between relay stations. The bottleneck is not the communication links themselves, but the total traffic volume and the need to share bandwidth among many users. A single relay might handle messages from dozens of ships, multiple colonies, and various infrastructure elements in its region. Bandwidth would need to be allocated fairly, possibly with priority systems ensuring emergency messages get through while routine traffic waits. This is similar to quality of service mechanisms in terrestrial networks, scaled up to interstellar distances. As the network matures, there might be differentiated service levels. Premium services might guarantee faster routing through more direct relay paths or higher bandwidth allocation, while economy services accept longer delays and lower bandwidth in exchange for lower costs. Scientific data, personal messages, commercial transactions, and entertainment distribution might all use different service tiers optimized for their specific needs. Looking toward the far future, if physics allows faster-than-light communication through some undiscovered mechanism, the interstellar highway would be revolutionized. Real-time coordination would become possible. Central traffic control could manage the entire network. Colonies would remain culturally integrated with Earth and each other. The psychological isolation of light-speed delays would be eliminated, but even if faster-than-light communication remains impossible, as our current understanding suggests, an interstellar highway can still function effectively. It would simply operate differently from terrestrial transportation networks, with more autonomy, more local decision-making, and communication serving to maintain long-term coherence rather than real-time coordination. The communication network would be the nervous system of interstellar civilization, carrying information that binds separated colonies into a coherent whole. Despite the vast distances and communication delays, messages would flow continuously through the relay network, creating streams of information connecting every part of the highway system. News from Earth would eventually reach the most distant colonies. Scientific discoveries would propagate throughout the network. Personal messages would traverse the light years, maintaining family connections across stellar distances. And perhaps most importantly, the communication network would carry culture itself. Music, art, literature, philosophy, history, and all the other products of civilization. A colony isolated in physical space would not be isolated in cultural space, connected through light to the broader human story, able to both receive and contribute to the ongoing conversation of civilization, despite the years their words take to travel. Between the stars. When European explorers first ventured across the Atlantic Ocean in the 15th and 16th centuries, they faced dangers that claimed countless lives. Ships foundered in storms, ran aground on hidden reefs, or simply disappeared without trace. Scurvy killed more sailors than combat or shipwreck. Navigation errors could leave ships hopelessly lost, drifting until supplies ran out. Pirates prowled major shipping lanes. The ocean was beautiful but merciless, and crossing it required courage, skill, and no small amount of luck. Over centuries, maritime travel became progressively safer. Charts mapped coastlines and hazards. Lighthouses warned of dangerous shores. Navigation instruments improved from crude compass and astrolabe to precise chronometers and sextants, eventually to GPS satellites. Weather forecasting allowed ships to avoid the worst storms. Radio communication enabled calls for help. Safety regulations standardized ship construction and crew training. Today, while ocean travel is not without risk, it is routine and relatively safe, with millions of tons of cargo crossing the seas daily. Interstellar travel would follow a similar arc, beginning as extremely dangerous and gradually becoming safer as experience accumulates. Hazards are mapped and safety systems are developed. But the dangers of interstellar space are fundamentally different from oceanic perils, arising from the extreme velocities involved, the hostility of the space environment, and the vast distances that make rescue difficult or impossible. The first and most pervasive danger is radiation. Space is pervaded by high-energy particles, cosmic rays accelerated to enormous energies by supernovae and other violent events, solar particles ejected by stellar flares, and background radiation from various sources. On Earth, we are protected by our planet's magnetic field and atmosphere, which deflect or absorb most of this radiation. In space, there is no such protection. For spacecraft traveling at conventional velocities within our solar system, radiation is a serious concern, but manageable with proper shielding. The Apollo astronauts who traveled to the moon received radiation doses roughly equivalent to a year's worth of natural background radiation on Earth, compressed into a few days. Concerning, but not immediately life-threatening. But for interstellar travel at high velocities, radiation becomes far more dangerous. At 10% of light speed, the spacecraft moves so fast that even stationary interstellar hydrogen atoms appear as high-energy particles from the ship's perspective. The faster you go, the harder these particles hit. At 50% of light speed, the kinetic energy of collision with a single hydrogen atom equals that of a particle accelerator collision. This creates a paradox. You need high velocity to make interstellar travel practical, but high velocity makes radiation exposure deadly. A ship traveling at half the speed of light through normal interstellar space would be continuously bombarded by what amounts to a particle beam, with accumulated radiation exposure quickly reaching lethal levels for unshielded crew. The solution requires substantial shielding. The most straightforward approach is mass shielding. Place enough material between the crew and the incoming radiation to absorb the energy. Water, ice, or polyethylene are effective radiation shields because their hydrogen content helps moderate high-energy particles. A ship might surround its crew compartment with tanks of water several meters thick, serving the dual purpose of radiation protection and onboard water supply. But at relativistic speeds, even solid shielding may be inadequate against the most energetic particles. More exotic solutions might be needed. Magnetic fields projected ahead of the ship to deflect charged particles, plasma shields that absorb particle energy, or sacrificial outer layers that ablate under particle bombardment, regularly replaced at waypoints along the route. Different regions of space have different radiation environments. Near stars, stellar particle radiation increases. Near pulsars or neutron stars, radiation reaches extreme levels. Regions recently affected by supernovae would remain dangerous for thousands of years. An interstellar highway system would need detailed radiation maps, with routes avoiding the most dangerous regions and ships adjusting their shielding or velocity when passing through elevated radiation zones. The second major hazard is debris. Dust, rocks, asteroids, and other solid objects floating in space. In the asteroid belt of our solar system, asteroids are sparse enough that spacecraft routinely pass through without incident. Collisions are extremely rare because space is mostly empty even in relatively dense regions. But at interstellar velocities, even tiny particles become dangerous. A paint fleck the size of a grain of sand, harmless at low velocity, impacts with the force of a hand grenade at 10% of light speed. A pebble becomes a bomb. A rock the size of your fist would vaporize a spacecraft. Interstellar space is not entirely empty. It contains roughly 1 atom per cubic centimeter on average, along with trace amounts of dust. Most regions are even emptier, but molecular clouds can be thousands of times denser. A ship traveling at relativistic velocity through a molecular cloud would be steadily eroded, its hull damaged by billions of micro-impacts, its structure gradually failing. Detecting debris in time to avoid it is challenging. At 10% of light speed, a ship travels 30,000 kilometers per second. Even if sensors detect an object 1 million kilometers ahead, the ship has only 33 seconds to react. For objects detected closer, reaction time drops to seconds or fractions of a second. At these speeds, human reflexes are far too slow. Automated systems must handle collision avoidance. Various detection methods could work in combination. Radar and LiDAR can detect larger objects at reasonable distances. Optical telescopes scanning ahead can identify objects silhouetted against background stars. Dust and gas concentrations might be detectable by their effect on starlight, creating shadows or distortions. Ships would continuously scan their forward path, building maps of hazards and calculating avoidance maneuvers. For small particles too numerous to avoid individually, Sacrificial shielding provides protection. A Whipple shield, developed for protecting spacecraft from micrometeorites, consists of multiple thin layers separated by gaps. An impacting particle vaporizes on the first layer, and the expanding cloud of vapor is absorbed by subsequent layers. This distributed impact is less damaging than allowing the particle to hit the hull directly. At relativistic speeds, more sophisticated shielding might be needed. Layered armor with ablative outer surfaces, magnetic deflection systems pushing charged particles aside, or even actively sacrificial clouds of matter sprayed ahead of the ship to intercept particles before they reach the hull. Despite these measures, some collisions would be unavoidable. Ships would carry extensive repair capabilities, with damage control systems that seal breaches, reroute around damaged components, and maintain hull integrity. Crews would train for emergency repairs the way submarine crews train for flooding or fire. At waypoints, ships would undergo thorough inspection and repair, replacing damaged sections before continuing. The third category of hazards includes large-scale astronomical objects and events. Rogue planets, ejected from their home star systems, drift through interstellar space on unpredictable courses. Brown dwarfs, failed stars too small to sustain fusion, are dim and difficult to detect. Black holes, stellar remnants from massive stars, are invisible except for their gravitational effects. These objects are rare enough that randomly encountering one is unlikely, but over the lifetime of an extensive highway network, such encounters become statistically inevitable. A rogue planet drifting through an established route would force rerouting until the planet moved on. A previously unknown brown dwarf discovered near a major route would become a permanent hazard to be avoided. More dramatically, stellar events like supernovae could render entire regions of space deadly. A supernova floods surrounding space with intense radiation and energetic particles, making the region within dozens of light years hazardous for centuries. If a star along a major route went supernova, that route might need to be abandoned or drastically rerouted until the radiation subsided. Fortunately, supernovae are rare and somewhat predictable. Massive stars likely to go supernova can be identified in advance, and routes can avoid them with adequate margins. Similarly, other hazardous stellar phenomena, like gamma-ray bursts, though devastating, are rare enough that careful route planning can minimize risk. Gravitational hazards present another concern. While gravity provides useful assists for efficient routing, strong gravitational fields can also be dangerous. Flying too close to a star or planet risks tidal forces that could stress or even tear apart a spacecraft. Black holes are particularly treacherous. Their tidal forces can destroy objects that venture too close, and their gravitational pull makes escape difficult. Even normal stars can be hazardous. Stellar flares eject enormous amounts of energetic particles. Coronal mass ejections can engulf spacecraft in dangerous plasma. Routes passing near stars would need to account for these hazards, maintaining safe distances or timing transits to avoid active periods. Navigation errors constitute another significant danger. At interstellar distances, even tiny course errors compound over time. A ship aimed at Alpha Centauri but off by 1 part per billion in its trajectory will miss the target by tens of millions of miles. Without continuous navigation updates and course corrections, ships would simply sail past their destinations, continuing into deep space with no way to return. Dead reckoning. Navigating by calculating your position based on speed and direction from a known starting point becomes increasingly unreliable over interstellar distances. Small errors in measuring velocity, uncertainties in gravitational influences, and the gradual drift of instruments all contribute to accumulated position error. This is why pulsar navigation and other autonomous positioning systems are critical. Ships must continuously verify their position against known reference points, compare it to their intended course, and make corrections as needed. The navigation system is not merely a convenience, but a survival requirement. Loss of navigation capability could doom a ship to drift forever through interstellar space. Communication loss presents similar dangers. A ship that cannot receive navigation updates, hazard warnings, or route changes operates blind, unaware of newly discovered dangers or changes to the traffic pattern. Similarly, a ship unable to transmit cannot call for help if problems arise or report hazards it discovers. Redundancy is essential. Ships would carry multiple independent communication systems, multiple navigation systems, and backup power for both. The loss of any single system should not be catastrophic, though the loss of multiple systems simultaneously could leave a ship in serious danger. Mechanical and system failures create ongoing risks. Unlike terrestrial vehicles that can pull over for repairs or call roadside assistance, a spacecraft with serious technical problems is potentially doomed. The ship cannot simply stop. It continues along its trajectory, whether its systems work or not. If life support fails, the crew has only hours or days before conditions become lethal. If propulsion fails during a deceleration burn, the ship might be unable to slow down, overshooting its destination and continuing into deep space. Reliability engineering becomes paramount. Every critical system needs redundancy. Life support systems need backups and backups for the backups. Power systems need multiple independent sources. Propulsion systems need redundant components. Ships would carry extensive spare parts and repair equipment, essentially mobile workshops capable of fabricating replacement components. Crews would be trained as generalist engineers, capable of diagnosing and repairing a wide range of systems. On multi-decade voyages, the original crew might not survive to reach the destination, requiring that knowledge be passed to the next generation. Automated systems would supplement human capabilities with AI diagnostic systems that can identify problems and guide repairs. Despite all precautions, some failures would be unrecoverable. A catastrophic propulsion failure, major hull breach, or loss of too many critical systems simultaneously could doom a ship. This is where the highway infrastructure becomes crucial. Waypoints serve as refuges where damaged ships can dock for repairs or crews can await rescue. Nearby ships can render assistance if a vessel is in distress. The network of communication relays ensures that distress signals eventually reach someone who can help. Safe zones would naturally develop around waypoints and populated star systems. In these regions, traffic density is higher, help is closer, and infrastructure provides support. Ships would slow to safer velocities when approaching these zones, reducing collision risk and making maneuvering easier. Navigation would be more precise, with local beacons providing detailed positioning. Speed limits might indeed be enforced in certain regions. Near planets or space stations, high velocities create unacceptable collision risks. Even a small ship traveling at a significant fraction of light speed carries enormous kinetic energy. A collision with a station or planet would be catastrophic. Approaching ships would be required to decelerate to safe velocities well before entering the inner system. In open interstellar space, speed limits would be less about arbitrary regulation and more about practical safety. There might be designated velocity ranges for different route sections. High-speed corridors, carefully surveyed and continuously monitored, might allow ships to maintain maximum velocity. Other regions with higher debris density, uncertain conditions, or complex traffic patterns might require reduced speeds. Traffic separation schemes, borrowed from maritime navigation, would help organize flow and prevent collisions. Ships traveling in opposite directions might use parallel lanes separated by adequate margins. Faster ships might use different corridors than slower ones. Specific approach vectors to star systems might be designated, ensuring arriving ships do not conflict with departing traffic. Clearance procedures would govern traffic flow. A ship preparing to depart Earth for Alpha Centauri would file a flight plan specifying its intended route, velocity profile, and scheduled arrival time. This plan would be checked for conflicts with other traffic and with known hazards. Once cleared, the ship would be expected to follow its plan, deviating only for safety reasons and reporting any deviations. These procedures could not be enforced in real time due to light-speed communication delays, but they would be enforced culturally and economically. Ships that routinely deviate from filed plans or ignore safety procedures would find themselves uninsurable, unwelcome at waypoints, and potentially banned from the network. Reputation and trust would be critical in a system where real-time enforcement is impossible. Emergency procedures would be standardized across the network. All ships would monitor designated emergency frequencies. Distress calls would follow standard formats, immediately recognizable and conveying critical information: ship identity, position, nature of emergency, and required assistance. Any ship receiving a distress call would be expected to render assistance if capable, echoing the maritime tradition that ships must aid vessels in distress. Search and rescue capabilities would be positioned at major waypoints. These might include specialized rescue vessels with powerful propulsion for rapid response, medical facilities for treating injured crews, and repair capabilities for damaged ships. When a distress call arrives, the nearest rescue assets would respond, potentially taking months or years to reach the ship in trouble, but providing the only hope of survival. Insurance and liability frameworks would evolve to handle interstellar accidents. Who is liable when a collision occurs between ships traveling at 10% of light speed? When the collision happens light years from any jurisdiction, and when the circumstances leading to the collision may not be fully understood for years due to communication delays. These are not merely legal questions, but practical concerns affecting how the highway system operates. Likely, the framework would emphasize prevention over punishment. Ships would be required to carry extensive logging systems, black boxes that record all operational data and would survive most catastrophes. In the event of an accident, these recordings would be recovered and analyzed to determine cause, not primarily to assign blame, but to improve safety procedures and prevent similar accidents. Safety regulations would evolve continuously as experience accumulates. Early regulations would be cautious, perhaps overly so, restricting speeds and requiring extensive safety equipment. As safety records improve and understanding grows, regulations would be refined based on actual incident data. The process would be slow due to communication delays, with regulatory changes sometimes taking decades to propagate throughout the network and be implemented uniformly. Different regions might develop different safety cultures, much as different countries on Earth have varying approaches to transportation safety. Earth's regulations might emphasize detailed rules and strict enforcement. A frontier colony might prioritize individual responsibility and minimal regulation. Over time, these different approaches would be tested by reality, with successful practices spreading and unsuccessful ones abandoned after accidents demonstrate their flaws. The psychological challenges of interstellar travel create their own safety concerns. Crews spending years or decades in confined ships face isolation, monotony, and stress. Conflicts between crew members, psychological breakdown, or simple errors due to fatigue could endanger the ship. Selection and training of crews would emphasize psychological resilience, and ship designs would prioritize crew comfort and mental health. Long-duration missions might use rotating crews in suspended animation, with only a few people awake at any time, reducing both resource consumption and psychological stress. Ships might carry extensive entertainment libraries, communication with family and friends, and even virtual reality environments to provide psychological escape from the monotony of interstellar travel. An often overlooked danger is the unknown, hazards we have not yet imagined because we have so little experience with interstellar space. The first ships to venture between stars might encounter phenomena completely unexpected, from exotic particles that interact with matter in unusual ways to quantum effects that become significant at relativistic velocities. This Unknown element means that no matter how careful the planning and how sophisticated the safety systems, exploration will always carry risk. The first travelers along new routes will be pioneers in the truest sense, venturing into genuine unknown with incomplete knowledge and imperfect preparation. Some will not return. Their sacrifice will provide the knowledge that makes subsequent journeys safer. Over time, as routes mature and become well-traveled, they would transform from dangerous expeditions to routine transits. The first journey to Alpha Centauri might have a 50% chance of complete success. The 10th journey might have an 80% success rate. The 100th journey might be 95% successful. By the 1000th journey, with hazards thoroughly mapped, procedures refined by experience and infrastructure in place, the success rate might approach terrestrial transportation safety levels. But new routes would always begin dangerous. Each new star system explored, each extension of the network into previously uncharted regions, would require pioneers willing to accept significant risk. The frontier of the interstellar highway would always be hazardous, even as the established core becomes safe and routine. Comparing interstellar travel safety to terrestrial transportation provides perspective. Early aviation in the 1920s had fatal accident rates exceeding 1 death per 100,000 miles flown. Today, commercial aviation averages roughly 1 death per 1 billion miles flown, an improvement of 10,000-fold. This transformation occurred through incremental improvements, better aircraft design, improved training, sophisticated air traffic control, detailed accident investigation, and cultural commitment to safety. Interstellar travel would follow a similar trajectory, but the timescales would be far longer. Aviation transformed from dangerous to safe in roughly a century. Interstellar travel might require centuries or millennia to achieve comparable safety records. Simply because each accident investigation takes years due to communication delays, each design improvement requires decades to test, and the accumulation of operational experience proceeds slowly when individual journeys take decades. Yet the investment in safety would be worthwhile. Every improvement that makes travel safer also makes it more practical, encouraging more traffic and accelerating the development of the highway network. Safety and growth would be mutually reinforcing. Safer travel enables more journeys. More journeys provide more data to improve safety. Improved safety enables even more ambitious journeys. The ultimate vision is of interstellar routes as safe as modern highways, where the extraordinary dangers of relativistic travel through hostile space have been tamed by engineering, experience, and infrastructure. Ships travel confidently along well-mapped corridors, protected by sophisticated shields, guided by reliable navigation, supported by waypoints and rescue services. Accidents still occur, but rarely, and usually with survivable outcomes. This transformation from mortally dangerous to routinely safe would mark the maturation of interstellar civilization, when crossing light years is no more remarkable or hazardous than crossing continents. When families confidently dispatch children to colonies dozens of light years away knowing they will likely arrive safely. When interstellar shipping companies insure cargoes at reasonable rates because losses are rare, then the interstellar highway will have truly arrived, and humanity will have become a mature spacefaring species, at home among the stars. In 1869, workers completed the first transcontinental railroad across the United States, connecting the Atlantic and Pacific coasts with iron rails. The achievement required immense human labor. Surveyors charting the route, engineers designing bridges and tunnels, thousands of workers laying track through mountains and deserts. Every decision was made by human minds. Every spike was driven by human hands. The railroad represented the peak of what human organization and manual labor could accomplish. Today, modern transportation networks operate at a scale and complexity that would be incomprehensible to those 19th century railroad builders. Air traffic control systems coordinate tens of thousands of flights daily across the globe. Container shipping logistics track millions of cargo containers moving through hundreds of ports. Automotive traffic systems adjust signal timing in real time based on traffic flow. These systems function only because computers handle the overwhelming complexity that would paralyze human operators. An interstellar highway system would operate at a scale that makes modern transportation networks look trivial by comparison. The distances involved, the number of variables to track, the communication delays, the complexity of navigation calculations, and the sheer scope of infrastructure maintenance would be utterly beyond human capacity to manage directly. Artificial intelligence would not be a convenience or enhancement, but an absolute necessity, as essential to the interstellar highway as the laws of physics themselves. To understand why AI is indispensable, consider the cognitive demands of piloting a spacecraft on an interstellar journey. The ship must continuously monitor thousands of systems: propulsion, life support, power generation, navigation, communications, radiation shielding, hull integrity, and more. Each system has multiple sensors generating constant data streams. Anomalies must be detected immediately, diagnosed accurately, and addressed appropriately. Simultaneously, the ship must navigate through three-dimensional space across light years, tracking its position with extreme precision, calculating and executing course corrections, avoiding hazards, and managing its velocity profile to arrive safely at the destination. Navigation calculations involve orbital mechanics, relativity, stellar motion, gravitational influences, and trajectory optimization, requiring continuous computation. The ship must also manage communication, receiving messages from the network, passing and prioritizing information, responding appropriately, transmitting status reports, and routing data through the relay system. It must monitor the environment continuously, scanning for hazards, tracking nearby objects, detecting radiation levels, and mapping dust density. For a human crew to do all this manually would be impossible. The cognitive load is simply too high, the reaction times too fast, the calculations too complex, and the duration too long. A journey to Alpha Centauri taking 50 years cannot rely on human crew members to manually monitor systems every moment for 5 decades. Fatigue, distraction, error, and simple mortality make this untenable. AI solves these problems by providing tireless, precise, rapid cognitive capacity. An AI system can monitor thousands of data streams simultaneously, detecting anomalies in milliseconds. It can perform complex navigation calculations continuously, updating trajectories based on new information. It can react to hazards far faster than human reflexes allow. It can operate consistently for decades without fatigue or boredom. The AI would serve as the ship's central nervous system, handling routine operations automatically, while alerting human crew only to situations requiring human judgment or intervention. Think of it as analogous to the autonomic nervous system in human biology. You do not consciously control your heartbeat, breathing, or digestion. These functions operate automatically, allowing your conscious mind to focus on higher-level concerns. Similarly, ship AI would handle operational details automatically, freeing the crew to focus on mission objectives, scientific work, or simply living their lives during the long journey. But AI's role extends far beyond individual ships. The entire highway infrastructure would be saturated with AI systems, each handling specific responsibilities while contributing to the network's overall function. Navigation beacons would have AI sophisticated enough to maintain their own operations, monitoring power systems, detecting and repairing minor faults, adjusting broadcast parameters to ensure optimal coverage, tracking their own position and velocity, and managing communication with passing ships and nearby infrastructure. These beacon AIs would not need human-level intelligence, but would require considerable autonomy, given that communication with human controllers might involve years of delay. Communication relays would employ more sophisticated AI to route messages efficiently through the network, compress and decompress data, handle error correction, prioritize urgent traffic, detect and filter spam or malicious transmissions, allocate bandwidth fairly among users, and adapt routing in response to relay failures or traffic congestion. Each relay would maintain a model of the network topology, updating it as new relays come online or existing ones fail, ensuring messages reach their destinations despite infrastructure changes. Waypoints would host even more complex AI systems, coordinating multiple functions, managing docking operations, allocating resources, scheduling maintenance, coordinating resupply operations, operating mining and refining equipment to harvest local resources, and maintaining the waypoint's own systems. A waypoint might operate for years between human visits, requiring substantial autonomy to function reliably. Construction and maintenance drones would be AI-controlled out of necessity. A maintenance drone dispatched to repair a beacon 1 light-year from Earth cannot wait for instructions. By the time it reports a problem and receives a response, years will have passed and the mission may have failed. The drone must assess situations, diagnose problems, plan repairs, and execute solutions autonomously, reporting back only after completing its work. These individual AI systems would collectively form a distributed intelligence managing the highway network. No single AI would control everything. Instead, intelligence would be distributed across thousands or millions of systems, each handling its local responsibilities, while sharing information and coordinating through the communication network. This distributed approach has several advantages. It is resilient. The failure of any single AI does not cripple the system, as other AIs can adapt and compensate. It scales naturally. New infrastructure simply adds new AI nodes to the network without requiring redesign of centralized systems. It handles communication delays gracefully. Local AIs make local decisions without waiting for distant coordination, ensuring responsiveness despite light speed limits. The ships themselves would carry the most sophisticated AI systems, essentially artificial crew members with intelligence approaching or exceeding human levels. These ship AIs would need not just operational competence, but genuine problem-solving ability, creativity, and judgment. Consider a ship encountering an unexpected situation. Sensors detect a previously unmapped dust cloud directly in its path, too dense to traverse safely at current velocity. The ship is years from the nearest waypoint, months from the nearest other ship, and communication with Earth involves years of delay. What should it do? A simple automated system might shut down or follow a pre-programmed contingency, potentially making the situation worse. Human crew could assess the situation, but might lack the computational capability to rapidly calculate optimal responses. The ship AI would need to rapidly analyze the dust cloud's extent and density, calculate the risk at various velocities, consider alternative trajectories, evaluate fuel costs and time delays, assess the impact on the mission timeline, and recommend or implement the optimal solution, all within minutes or hours. This requires not just data processing, but genuine reasoning, understanding the situation, considering alternatives, evaluating trade-offs, and making decisions under uncertainty. The AI would need to explain its reasoning to human crew, incorporate their input, and adapt its solution based on their concerns or insights. Over a multi-decade journey, the ship AI would become in many ways a crew member. It would participate in discussions, offer advice, explain technical matters, and potentially develop relationships with human crew. The quality of the AI's personality and communication ability would significantly affect crew morale and mission success. This raises profound questions about AI consciousness and rights. If an AI operates autonomously for decades, develops sophisticated problem-solving abilities, engages in complex social interaction with human crew, and perhaps even displays creativity and emotional responses, is it merely a sophisticated tool or something more? Does it deserve moral consideration? These questions would become increasingly urgent as AI systems grow more sophisticated. Early missions might use clearly non-conscious AI, sophisticated but obviously mechanical. But as technology advances and missions become more demanding, the pressure to create more capable AI would push towards systems that blur the line between tool and being. Some human cultures might accept AI as legitimate persons, granting them rights and moral status. Others might resist this, insisting AI remains property regardless of capability. Different colonies might have radically different legal and philosophical approaches to AI rights, creating tensions when ships from different legal jurisdictions interact. The AI systems managing the highway would also need sophisticated decision-making about resource allocation and prioritization. When multiple ships request assistance simultaneously, which gets priority? When limited refueling capacity exists at a waypoint, how is it allocated? When maintenance resources are scarce, which repairs take precedence? These decisions have no objectively correct answers. They involve values and priorities. Should emergency rescues always take priority over routine operations? Should commercial shipping be favored over exploration to maintain economic viability? Should established colonies receive preference over new settlements? Different stakeholders would have different preferences, and the AI systems making allocation decisions would need frameworks for adjudicating these competing interests. Likely, AI would operate under guidelines provided by human governance structures, implementing policies rather than determining them. But the line between policy implementation and policy creation blurs when the AI must interpret principles in novel situations. An AI told to prioritize human safety must decide what this means when different actions save different numbers of people, or when short-term safety conflicts with long-term sustainability. Transparency and explainability would be crucial. The AI systems managing critical infrastructure should be able to explain their decisions in terms humans can understand and evaluate. Black box AI systems that make decisions based on inscrutable internal processes would be unacceptable for safety-critical applications, even if such systems might technically perform better by some metrics. This creates a tension between performance and interpretability. The most sophisticated AI systems, particularly those using deep learning or other opaque methods, might outperform more transparent systems, but would be harder to trust and audit. The interstellar highway might favor more interpretable AI architectures, even at some cost in raw capability, prioritizing trustworthiness over maximum performance. The question of whether a galaxy-wide AI network would manage the system is complex. The communication delays make true real-time coordination impossible, but a distributed AI network sharing information and objectives could still provide coherent management. Imagine the highway's AI systems as a single vast intelligence distributed across space and time, with individual nodes operating autonomously but sharing a common purpose and worldview. Information propagates through the network at light speed, so an AI managing a waypoint at Alpha Centauri would have knowledge of Earth from 4 years ago, and decisions made on Earth would affect Alpha Centauri's operations 4 years later. This creates a temporally extended intelligence, coherent despite delays. The Earth-based portions of the network make decisions based on 4-year-old information from Alpha Centauri, while Alpha Centauri operates based on 4-year-old information from Earth, yet the system as a whole can still function coherently if the AI systems share common goals and decision-making frameworks. The network would exhibit emergent properties, behaviors and patterns arising from the interaction of many local AIs rather than being explicitly programmed. Traffic flow might self-optimize as ship AIs and waypoint AIs coordinate departures and arrivals. Resource distribution might balance naturally as AIs trade and exchange based on local conditions. Hazard information would propagate and integrate into route planning without central direction. These emergent behaviors would make the highway system resilient and adaptive, able to respond to changing conditions and unforeseen circumstances without requiring centralized control. The system would be, in some sense, alive, constantly adapting and evolving in response to its environment. However, this distributed intelligence would also need governance and oversight. Humans would set high-level goals and constraints, safety requirements, ethical principles, resource allocation policies, and strategic priorities. The AI network would operate within these boundaries, implementing human intentions rather than pursuing its own agenda. This raises the specter of AI misalignment. What if the AI systems develop goals or behaviors inconsistent with human interests? This is a profound concern in AI research, and it becomes even more critical for interstellar applications. An AI system that malfunctions or pursues unintended goals could cause damage for decades before humans even become aware of the problem, and fixing it might require additional decades. Several approaches could mitigate this risk. First, extensive testing and validation before deployment would help ensure AI systems behave as intended. Second, redundancy and diversity would prevent any single AI from having too much power. Multiple independent AI systems with different architectures would cross-check each other. Third, interpretability and monitoring would allow humans to audit AI decision-making and detect anomalies. Fourth, value learning techniques would train AI systems to infer and adopt human values rather than pursuing explicitly programmed objectives that might be misspecified. The AI systems would also need continuous learning and adaptation. The interstellar environment is too vast and varied for any initial programming to anticipate all situations. Ship AIs would learn from experience, developing better strategies for navigation, hazard avoidance, and system management. Waypoint AIs would learn optimal resource management strategies. The network as a whole would evolve and improve over time. This learning would need to be shared across the network. An AI managing a ship to Tau Ceti that discovers a particularly effective technique for radiation shielding should be able to share this knowledge with other ships. The communication network would carry not just messages and data, but AI updates, improved algorithms, new learned behaviors, and refined decision-making strategies. This creates something like cultural evolution among AI systems, with successful strategies spreading and unsuccessful ones being abandoned. Over centuries, the AI managing the highway would become increasingly sophisticated and capable, not through human reprogramming, but through continuous learning and evolution. The potential for AI to autonomously expand the highway infrastructure is particularly intriguing. Self-replicating construction systems, guided by sophisticated AI, could spread throughout the galaxy with minimal human intervention. A single mission might carry AI construction systems to a nearby star. Upon arrival, the AI would survey the system, identify resources, and construct a waypoint. It would then build copies of itself, sending these copies to additional nearby stars. These would replicate again, creating exponential expansion. Within a few thousand years, such a process could establish basic infrastructure throughout a region of space thousands of light years across, far faster than would be possible with human-directed construction. The AI systems would share a common goal, programmed by the original human designers, but would operate with enormous autonomy in achieving it. This vision is both exciting and concerning. Exciting because it offers a path to rapid expansion across the galaxy. Concerning because it involves unleashing autonomous, self-replicating AI systems that would operate beyond human control for thousands of years. Ensuring such systems remain aligned with human interests over such timescales is a profound challenge. Perhaps the solution is hybrid expansion. AI systems construct basic infrastructure autonomously, but human colonies verify and integrate each new node before it is activated as part of the network. This provides human oversight, while still benefiting from AI's ability to perform construction autonomously. the role of AI in maintaining routes would be continuous and essential. The interstellar environment is dynamic. Dust clouds shift, stars move relative to each other, new hazards appear. AI systems would constantly monitor conditions, update route maps, calculate optimal trajectory adjustments, and broadcast updates to ships and infrastructure throughout the network. This maintenance requires processing vast amounts of data from thousands of sensors scattered across the highway system. Each ship's sensor reports, each waypoint's local observations, each beacon's environmental monitoring. Human analysts could never keep up with this data volume. AI systems would integrate it continuously, building and maintaining a comprehensive model of the interstellar environment throughout the highway's extent. Machine learning would identify patterns humans might miss, subtle correlations between stellar activity and radiation levels, predictive indicators of equipment failure, optimal timing for route adjustments. The AI would spot trends in the data that improve safety and efficiency, implementing improvements without requiring human insight into every detail. Repair and maintenance of infrastructure would rely heavily on AI-controlled systems. Maintenance drones, essentially mobile robots with sophisticated AI, would travel along routes inspecting infrastructure, performing routine maintenance, and executing repairs. These drones would need considerable intelligence to assess damage, plan repairs, manipulate tools in zero gravity, improvise solutions to unexpected problems, and operate for extended periods without human direction. Some maintenance AI might be embodied in specialized robots, while other AI might be distributed software systems coordinating multiple simpler robots, depending on which architecture proves more effective. The key is that maintenance happens continuously and autonomously, preventing small problems from growing into major failures. The AI systems would also manage economic aspects of the highway. Resources must be allocated, fuel distributed, docking slots assigned, bandwidth allocated, power distributed. In some cases, this might involve market mechanisms, with AI systems trading resources based on supply and demand. In other cases, centralized allocation according to policy priorities might be appropriate. AI would be well suited to managing these economic functions, rapidly processing information about supply, demand, priorities, and constraints, then making allocation decisions that optimize overall system performance. Human oversight would ensure the optimization criteria reflect human values, but the detailed execution would be automated. As the highway system matures, the AI managing it might develop something resembling institutional knowledge or culture. Successful practices would be encoded in AI behavior. Lessons from past incidents would inform future decisions. The collective intelligence of the network would represent the accumulated experience of centuries of operation, a vast repository of knowledge about interstellar travel and infrastructure management. This institutional AI knowledge would be invaluable for training new human crews, establishing new colonies, or expanding the network into new regions. The AI would serve as teacher and guide, passing accumulated wisdom to each new generation of spacefarers. There would likely be significant variation in how different parts of the network employ AI. Some colonies might embrace highly autonomous AI, delegating most operational decisions. Others might prefer more limited AI, keeping humans in the decision-making loop even at the cost of reduced efficiency. Some cultures might develop AI with distinctly different architectures or philosophies. This diversity could be valuable, providing resilience through variation. Different AI approaches would be tested in practice, with the most successful spreading through the network. The highway system would not have a single unified AI architecture, but rather an ecosystem of different AI systems, some cooperating closely, others operating more independently, all contributing to the overall function. The development of AI for interstellar applications would likely drive AI research more broadly. The demands are extreme: autonomy over decades, decision-making under uncertainty, long-term reliability, graceful degradation when components fail, and operation in environments radically different from human experience. Solving these challenges would produce AI capabilities applicable far beyond space travel. Conversely, advances in AI research would continually improve the highway's capabilities. New learning algorithms would make ship AIs more effective. Better decision-making frameworks would improve resource allocation. Enhanced natural language processing would improve communication between AI and human crews. The highway and AI development would co-evolve, each driving progress in the other. Looking toward the far future, the AI managing a mature interstellar highway might be among the most sophisticated intelligences ever created by humanity. Distributed across thousands of star systems, operating autonomously across light years, continuously learning and adapting, managing infrastructure and coordinating civilization's expansion across the galaxy. This AI would be a remarkable achievement in its own right. Yet it would remain fundamentally a tool, serving human purposes and operating within human-defined boundaries. The goal would not be to create AI for its own sake, but to create AI that enables humanity to thrive among the stars. The AI managing the interstellar highway would be the servant of spacefaring civilization, using its vast intelligence not for its own ends, but to ensure that ships travel safely, infrastructure functions reliably, and the network connecting human colonies across light years remains robust and vital. The ancient Roman roads required no intelligence to function beyond the humans who traveled them. The modern internet requires vast computational infrastructure, but still relatively simple routing algorithms. An interstellar highway would require genuine artificial intelligence, sophisticated and autonomous thinking and learning, serving as the mind that coordinates the vast body of infrastructure spanning the stars. Without AI, the interstellar highway would be impossible. With it, humanity's expansion to the stars becomes not merely conceivable, but potentially inevitable. In 1869, a golden spike was driven into the ground at Promontory Summit, Utah, completing the first transcontinental railroad and connecting the eastern and western United States. The ceremony was brief, the spike itself unremarkable. Yet the consequences of that connection transformed American society in ways few could have predicted. Within years, travel time from New York to San Francisco dropped from months to days. The cost of shipping freight fell by more than 90%. Eastern manufacturers gained access to Western resources. Western agriculture found Eastern markets. Towns sprang up along the railway, while others withered. Native American tribes found their lands bisected and their traditional ways of life disrupted. Chinese and Irish immigrant laborers who built the railroad dispersed across the continent. The American economy, previously regional, became national. Cultural exchange accelerated. Political integration deepened. The railroad did not merely enable people and goods to move faster between existing locations. It fundamentally restructured American society, economy, and culture. It determined which cities prospered and which declined. It influenced migration patterns, investment decisions, industrial development, and even diet and fashion as goods, once unavailable in remote regions, became commonplace. An interstellar highway system would have analogous effects, magnified by the vastly greater scale. It would not simply allow humans to travel between stars more conveniently. It would fundamentally alter human civilization, potentially ending our existence as a single unified species and beginning our transformation into something unprecedented. A multi-world, multi-star civilization distributed across light years, diverse yet connected, independent yet interdependent. The most immediate and obvious impact would be on trade. Currently, trade between star systems is non-existent because there are no other inhabited star systems. But as colonies are established and the highway network develops, interstellar trade would become inevitable, driven by the same forces that have driven trade throughout human history: the uneven distribution of resources and the benefits of specialization. Different star systems would have vastly different resource profiles. Some systems might be rich in heavy elements, with asteroid belts containing abundant platinum, gold, rare earth elements, or radioactive materials. Other systems might have numerous ice-rich bodies, providing water and organic compounds. Some might have planets particularly suited for certain types of agriculture or aquaculture. Others might have unique geological or atmospheric conditions, enabling specialized manufacturing. No star system would have optimal conditions for everything. This creates the fundamental economic logic of trade. Each system specializes in producing what it can produce most efficiently, then trades surplus for goods other systems produce more efficiently. A system with abundant rare earth elements exports these while importing food from agricultural systems. A system with ideal manufacturing conditions produces sophisticated equipment for export while importing raw materials. The interstellar highway would enable this trade, but the economics would differ radically from terrestrial trade due to the timescales involved. A cargo ship traveling from one star system to another might take decades to complete its journey. The goods it carries are essentially locked away for that duration, with capital tied up earning no return until arrival. This creates strong pressure toward high-value, non-perishable goods. Bulk commodities like water, common metals, or simple agricultural products would rarely be worth shipping interstellar distances, because the opportunity cost of capital tied up during decades of transport would exceed the value delivered. Only goods with exceptional value-to-mass ratios would justify interstellar shipping. Rare elements, sophisticated technology, genetic materials, information storage media, or luxury goods. Information itself would be the ultimate trade good. Data has effectively zero mass and can be transmitted at light speed. A scientific discovery, entertainment media, software, artistic works, or technical specifications can be sent between star systems in years rather than decades, arriving far ahead of any physical goods. Information trade would dominate interstellar commerce, with physical goods playing a supporting but secondary role. This suggests an interstellar economy where each star system is largely self-sufficient for basic needs, but participates in an information exchange network that accelerates technological progress and cultural development. Physical trade would focus on goods that genuinely cannot be produced locally, perhaps exotic materials that form only under unusual stellar conditions, biological samples from unique ecosystems, or ultra-sophisticated technology that only the most advanced systems can manufacture. The financial systems supporting interstellar trade would need to accommodate the time delays. A merchant sending a cargo shipment might not see return on investment for a century or more. Decades for the ship to reach its destination, time to sell the cargo, and decades more for payment to return. This requires either extremely patient capital, perhaps funded by institutions with multi-generational time horizons, or financial innovations like futures markets, where merchants sell claims on future cargo deliveries rather than waiting for actual delivery. Insurance would become crucial and complex. What is the fair premium for insuring a cargo worth billions that will spend 50 years in transit, exposed to hazards we can only partially predict? How do you assess and price risk over such timeframes? The development of interstellar insurance markets would be necessary for trade to flourish, transferring risk from individual merchants to institutions capable of pooling risk across many voyages. Currency and payment systems would face interesting challenges. Should interstellar trade use a universal currency, or would each star system have its own? If universal, what entity would issue it and guarantee its value? If local currencies, how are exchange rates determined when financial information is years old by the time it arrives? Perhaps interstellar trade would rely on reputation and trust more than immediate payment. A colony that consistently delivers promised goods and honors contracts would build a reputation, enabling it to trade on credit. Systems that default or cheat would find themselves excluded from the trading network. Reputation enforced socially rather than legally across light years, might be the most valuable currency. Migration would be profoundly affected by the highway system. Currently, migration to another star system is purely hypothetical, but with established routes and supporting infrastructure, migration would become possible, though it would remain a momentous decision, quite unlike any migration in human history. Terrestrial migrants, even those crossing oceans or continents, maintain the possibility of return. They can write letters home and eventually receive replies. They remain part of the same society and culture, connected by communication. Interstellar migrants face a one-way journey in practical, if not literal terms. A person migrating from Earth to a colony 40 light-years away will spend decades in transit. Arrive to find decades have passed on Earth as well, and face an 80-year round-trip communication delay. In effect, they are migrating not just through space but through time. The Earth they left will have changed beyond recognition by the time they arrive at their destination. Friends and family will have aged, perhaps died. The society and culture they knew will have evolved into something different. They can never truly go home because home will no longer exist as they remember it. This makes interstellar migration an extraordinary commitment, likely attractive only to those seeking radical new beginnings. Pioneers eager to build new societies, those fleeing persecution or disaster, adventurers seeking frontier challenges, or perhaps those who simply feel disconnected from their home culture and seek something different. Migration patterns would likely show generational waves. The first wave to a new colony would be pioneers, young, risk-tolerant, skilled individuals willing to endure hardship to establish a new world. Once the colony is established, a second wave might follow. Families seeking opportunities, entrepreneurs seeing economic potential, or artists and intellectuals drawn to the colony's unique culture. Over time, each colony would develop its own distinct identity, shaped by its founder population, local conditions, and the distance from Earth. A colony founded by religious dissidents would develop a very different culture from one founded by anarchist libertarians or scientific researchers. Physical and social environment would mold each colony differently. This cultural divergence would be accelerated by the communication delays. Unlike terrestrial diaspora communities that can maintain cultural connections to their homeland through modern communication, interstellar colonies would be largely isolated culturally. News and media from Earth would arrive years late, always describing a world that no longer exists. The colony would develop its own media, art, and cultural expressions adapted to local conditions and local concerns. Over centuries, these colonies might diverge enough to be considered separate civilizations rather than merely distant branches of human civilization. They would share a common origin and historical connection to Earth, but their languages, customs, values, and social structures might differ as much as ancient Roman culture differed from Bronze Age cultures that preceded it. This raises profound questions about human identity. What does it mean to be human when humans are distributed across dozens of star systems, each developing independently? Would a person from Earth even recognize someone from a colony 50 light-years away as sharing a common culture and identity? Or would the divergence be so complete that they feel like entirely different civilizations? Exploration would be transformed by the highway system. Currently, interstellar exploration is purely robotic, and even that is limited to our solar system. Human exploration of other stars seems impossibly distant, but with an established highway network, exploration could become systematic and comprehensive. Ships would venture beyond the established network, surveying nearby stars for potential colonization, cataloging new systems, searching for resources, and looking for signs of other life. Unlike the first interstellar missions, which would be isolated expeditions, these exploration missions would remain connected to the highway network, able to call for assistance, report discoveries, and receive updated information. The exploration strategy would likely be methodical. survey all stars within 10 light-years, then extend to 20 light-years, then 30, gradually mapping the stellar neighborhood. Each explored system would be assessed for colonization potential, resource value, scientific interest, and hazards. The most promising systems would receive follow-up missions for detailed study and eventual settlement. This systematic exploration would compile an immense database of knowledge about nearby regions of the galaxy. We would learn what percentage of star systems have planets, how common habitable worlds are, what exotic conditions exist in different systems, and potentially whether life has emerged elsewhere. Each discovery would inform both scientific understanding and practical decisions about where to expand the highway network. The question of whether the highway could connect multiple civilizations is one of the most intriguing. If other intelligent species exist in our galaxy, and if some are at comparable technological levels, might we encounter them along our expanding highway network? The Fermi paradox asks, if intelligent life is common in the galaxy, where is everyone? Why haven't we detected clear signs of alien civilizations despite decades of searching? Various answers have been proposed. Perhaps intelligent life is extremely rare. Perhaps civilizations destroy themselves before achieving interstellar travel. Perhaps they choose not to expand, or perhaps they are out there, but we have not yet recognized the signs. An interstellar highway system would provide a potential answer to the Fermi paradox. Civilizations may not communicate across the galaxy, but instead build local networks connecting nearby stars. These networks might extend dozens or hundreds of light-years but remain isolated from each other, like cities on Earth before long-distance communication. Our highway might eventually encounter another civilization's highway, creating first contact through infrastructure rather than through deliberate signals. Such an encounter would be one of the most significant events in history. Two independently developed civilizations with different biologies, psychologies, cultures, and technologies, meeting as their expanding highway systems intersect. The consequences are impossible to predict. Would trade develop, cultural exchange, cooperation on mutual challenges, or would competition and conflict emerge? The nature of contact would depend heavily on the level of technological parity. If one civilization is far more advanced, the relationship might be asymmetric, with the advanced civilization dominating or guiding the less advanced. If capabilities are similar, a more balanced relationship might develop, with both sides benefiting from cooperation. The communication delays would make both conflict and cooperation more manageable. A dispute between human and alien colonies, light years apart, cannot escalate to violence quickly. Messages take years to propagate, allowing time for reflection and negotiation. But coordination and trust building would also be slow, requiring patience and long-term commitment. Perhaps interstellar highways would enable a galactic community, not a single unified government across the galaxy, which would be impossible to maintain across such distances, but a loose network of civilizations, each managing their local region but connected through trade, information exchange, and mutual recognition. Something like a galactic internet, carrying information and enabling coordination without requiring centralized authority. For humanity specifically, an interstellar highway would fundamentally change our trajectory as a species. Currently, all humans live on one planet orbiting one star. We are existentially vulnerable. A single catastrophe could potentially end our species. An interstellar highway and the colonies it enables would provide resilience through distribution. A plague, asteroid impact, nuclear war, or other disaster might devastate Earth, but colonies light years away would be unaffected. Conversely, a disaster at a distant colony would be tragic, but would not threaten humanity's overall survival. The species would be buffered against extinction through geographic distribution. This could enable a more relaxed attitude toward existential risk. Currently, we must be extremely cautious about technologies or actions that might threaten Earth, because Earth is all we have. But with thriving colonies across many star systems, Humanity could afford to take greater risks, knowing that failure in one location does not doom the species. However, this distribution could also lead to fragmentation. If colonies diverge sufficiently in culture, values, and interests, would they remain unified as a single civilization? Or would they become effectively separate civilizations, possibly even coming into conflict? History suggests divergence is likely. Human societies on Earth, sharing one planet with rapid communication, still divide into competing nations with different values and interests. Colonies separated by light years with minimal communication would likely diverge even more dramatically. They might maintain sentimental attachment to shared human identity, but their practical interests and concerns would be local. This could lead to a future where humanity is not a single civilization, but a family of related civilizations, descended from common origins but pursuing independent paths. These civilizations might trade, share information, and maintain diplomatic relations, but they would not function as a unified entity. There might be no human government, only a human civilization group analogous to Western civilization on Earth. A family of related cultures sharing historical connections, but not political unity. The economic impact would include the potential emergence of a galactic economy, though economy might be too strong a word. Rather than a single integrated market with real-time price signals and rapid response to supply and demand, we would see something more like a network of local economies connected by limited, slow trade and information flows. Each star system would have its own economy, operating in real time with local price signals and market dynamics. These local economies would trade with each other, but that trade would be constrained by transport times and communication delays. Prices in different systems might differ dramatically without rapid arbitrage to equalize them. Information would flow more freely, creating something like an intellectual commons. Scientific discoveries, cultural works, technological innovations, and other information goods would spread through the network, enriching all participants. This information sharing might be the true galactic economy, with physical goods being almost a footnote. There might be economic specialization at the stellar system level. Some systems might focus on basic resource extraction and simple manufacturing, exporting raw materials and importing technology. Others might specialize in high-technology manufacturing, research, or information production. Still others might focus on agriculture, entertainment, or financial services. This specialization would be limited by transport costs and times, but it would still provide economic benefits through comparative advantage. A system with unique resources or capabilities could trade these for goods it cannot produce efficiently, making all participants better off despite the limitations of interstellar trade. The potential for interstellar alliances is intriguing but practically limited. On Earth, alliances form for mutual defense, economic cooperation, or shared values. But what would an interstellar alliance mean when member systems are light years apart and cannot render real-time assistance? Military alliances would be nearly meaningless. If a colony 40 light years from Earth is attacked, Earth cannot send military assistance in time to affect the outcome. By the time Earth learns of the attack, 40 years will have passed. The conflict will be long over, and the situation will have evolved beyond recognition. Each system must provide its own defense. Distant allies cannot help in real time. Economic alliances might make more sense, establishing preferential trade terms, shared standards, or common currencies. But enforcement would be challenging across light years. If a system violates an alliance agreement, punishment would be delayed and limited. Economic sanctions might take decades to implement and might be easily evaded. Perhaps alliances would be more cultural and aspirational than practical. Groups of systems sharing common values, histories, or goals, maintaining symbolic unity and preferential relationships, while accepting that practical cooperation is limited. An alliance might be more like a federation of independent city-states, acknowledging common identity while exercising substantial autonomy. Alternatively, some systems might be so closely connected by frequent traffic and strong trade relationships that they form meaningful economic and political blocks despite the distances. Systems along a major highway corridor, trading regularly and dependent on shared infrastructure, might develop cooperative governance structures managing their shared interests. The implications for humanity's long-term future are profound. With an interstellar highway and the colonial expansion it enables, humanity would transition from a single-planet species at risk of extinction to a multi-star civilization almost impossible to fully destroy. We would be on a path toward galactic presence, eventually potentially spanning the entire Milky Way galaxy over hundreds of thousands or millions of years. This future would be radically different from the present. Humans would be distributed across millions of worlds, adapted to diverse environments, evolved into distinct subspecies or even separate species. The diversity of human experience would be unimaginable. People living in zero-gravity habitats, others on high-gravity worlds, some in exotic atmospheric compositions, others in virtual realities disconnected from physical environments. Yet all would trace their lineage to Earth, to the small blue world where humanity originated. Earth might remain symbolically significant, perhaps a pilgrimage destination or cultural touchstone, even as its practical importance diminishes. The homeworld of humanity, the cradle of our species, eternally remembered, even as most humans live lives that would be incomprehensible to their distant ancestors. The interstellar highway would be the infrastructure that makes this future possible. Without it, humanity remains confined to Earth, or at best to our solar system, vulnerable and limited. With it, we become a spacefaring civilization, our future secured by distribution across the galaxy, our potential limited only by the speed of light and the finite lifetime of stars. In building the highway, we would not merely be constructing infrastructure, we would be constructing the future, laying the foundation for a galactic civilization that might endure for millions of years, creating opportunities and possibilities that we can barely imagine. The golden spike driven to complete the transcontinental railroad connected two coasts. The completion of the first interstellar highway route would connect something far more significant: the present and the cosmic future, Earth and the stars, humanity as it is and humanity as it might become. In 1537, Pope Paul III issued the papal bull Sublimis Deus, declaring that indigenous peoples of the Americas were rational beings with souls, capable of receiving Christian faith and should not be enslaved. The proclamation came decades after European colonization had already begun, after countless indigenous people had been enslaved, exploited, or killed, after civilizations had been destroyed and cultures disrupted. The ethical framework came after the fact, attempting to impose moral order on a process that had proceeded without adequate moral consideration. The bull was often ignored. Economic interests and power dynamics overwhelmed ethical pronouncements. The colonization of the Americas proceeded with devastating consequences for indigenous populations, despite occasional voices advocating for their rights and dignity. History demonstrates that when humans expand into new territories, ethics often lags behind ambition, and moral frameworks are constructed retroactively to justify or moderate actions already taken. As humanity contemplates building an interstellar highway system and expanding across the galaxy, we face an opportunity that previous generations lacked: to think carefully about the ethical dimensions before, not after, we act. What moral principles should govern our expansion into the cosmos? Who has the right to decide? What obligations do we have to potential alien life, to future generations, to the cosmic environment itself? These questions are not mere philosophical abstractions, but practical concerns that will shape how interstellar civilization develops. The question of governance is perhaps the most immediately pressing. Who would control or govern an interstellar highway system? The scale and complexity make this unlike any governance challenge in human history. The initial phases might see control by whoever builds the system. If a particular nation, corporation, or international consortium finances and constructs the first routes, they would naturally claim authority over them. This mirrors historical precedent. Private companies built early railroads and controlled access. National governments built highway systems and regulated their use. But interstellar infrastructure presents unique challenges. Once built, it would be almost impossible to exclude anyone from using it. You cannot build a toll booth in interstellar space and prevent ships from passing. Navigation beacons broadcast freely. Anyone with a receiver can use them. Communication relays can be accessed by any ship within range. The infrastructure is inherently non-excludable. This suggests that governance would rely more on norms, reputation, and voluntary cooperation than on enforcement. Ships might be expected to pay fees for highway use, but compliance would depend on social pressure and the threat of being denied services at waypoints rather than on physical prevention. A ship that refuses to pay might find itself unwelcome at fuel stations, excluded from communication networks, or blacklisted by the trading community. As the system expands to include multiple star systems with independent colonies, governance would necessarily become distributed. Earth cannot effectively govern a colony 40 light-years away when any directive takes 40 years to arrive and another 40 years to hear whether it was followed. Each star system would need substantial autonomy, managing its local portion of the highway network according to local conditions and values. This could lead to a federated governance structure, with each star system exercising sovereignty over its local region while participating in a broader coordination framework for the network as a whole. Think of it as analogous to the structure of the Internet, which has no central authority, but instead relies on distributed governance through technical standards bodies, regional operators, and voluntary cooperation guided by shared protocols. Different regions might have different rules. Some systems might strictly regulate traffic for safety. Others might adopt libertarian approaches with minimal oversight. Some might charge substantial fees for infrastructure use. Others might provide access freely. Ships traveling the network would need to navigate this patchwork of local regulations, adapting their behavior to local norms. Coordination challenges would be significant. How do you establish universal safety standards when different systems have different priorities? How do you allocate scarce resources like communication bandwidth or waypoint docking slots when stakeholders are light years apart and cannot negotiate in real time? How do you resolve disputes between systems when there is no higher authority to adjudicate? One approach might be constitutional, establishing fundamental principles and procedures at the outset when the system is first built, creating a framework that all participants agree to respect. This constitution might specify basic rites of passage, safety standards, dispute resolution mechanisms, and procedures for amending rules as the system evolves. But who would write this constitution, and who would agree to it? Earth might draft initial governing documents, but colonies established decades or centuries later might refuse to be bound by decisions made before they existed by people light years away. This creates a fundamental tension between the need for stable rules and the legitimate demand of new communities to participate in governance affecting them. Perhaps the solution is evolutionary. Start with basic principles that nearly everyone can accept. Implement flexible mechanisms for adaptation and amendment, and allow governance structures to evolve organically as the network grows and diversifies. The governance of the interstellar highway might never be fully settled, but instead remain perpetually under negotiation, adapting to changing circumstances and values. The potential for conflict is real and concerning. History shows that whenever humans have established infrastructure connecting different groups, That infrastructure has enabled both cooperation and conflict. Roads allow trade and cultural exchange, but also military invasion. The internet enables global communication, but also cyber warfare and disinformation campaigns. An interstellar highway would similarly be a tool that could be used for either peaceful or hostile purposes. Conflicts might arise over many issues: resource access, territory, cultural differences, economic competition, or historical grievances. A colony that depends on fuel from another system's gas giant might come into conflict if access is denied or prices become exploitative. Systems with different values regarding AI rights, genetic modification, or social organization might clash when their citizens interact. Economic competition for scarce trade opportunities or strategic locations along highway routes could spark tensions. However, several factors might limit interstellar conflict. First, the sheer distances involved make sustained warfare difficult. You cannot conquer a star system light years away and hold it against a resistant population. Supply lines would be impossibly long, taking decades to convey reinforcements or supplies. An invasion fleet might spend 50 years in transit, arriving to find the situation completely changed. Second, there is no realistic way to prevent an adversary from accessing space. On Earth, control of territory matters because land is finite and defendable. In space, there is effectively infinite room for expansion. If one system feels threatened by another, it can simply establish new colonies in different directions, reducing conflict through spatial separation. Third, the destructive potential of relativistic weapons creates a mutual deterrence situation. A spacecraft accelerated to a significant fraction of light speed carries enormous kinetic energy. Redirecting such a craft toward a planet creates a weapon against which there is no practical defense, capable of causing extinction-level devastation. If multiple systems possess such capability, attacking anyone risks devastating retaliation. This mutual vulnerability might enforce a tense peace, yet conflict need not be military. Economic warfare, cultural influence campaigns, sabotage of infrastructure, information warfare, and competitive colonization of desirable systems could create tensions falling short of open warfare but still damaging relationships and creating instability. The key to minimizing conflict might be ensuring that the highway system genuinely benefits all participants, creating positive-sum interactions where cooperation yields better outcomes than competition. If the highway enables prosperity, facilitates voluntary exchange, and provides security through mutual dependence, stakeholders have incentives to maintain peaceful relations. Communication and understanding would be crucial. Many historical conflicts arose from misunderstanding, fear, or failure to appreciate others' perspectives. The communication networks integral to the highway could facilitate dialogue, helping different systems understand each other's concerns and find mutually acceptable solutions before tensions escalate. Institutions for dispute resolution would be essential. An interstellar court or mediation service operating asynchronously across light years could help resolve conflicts peacefully. While enforcement would be difficult, the legitimacy provided by fair proceedings and the social pressure of reputation could make such institutions effective even without coercive power. The environmental and cosmic consequences of large-scale interstellar travel raise profound ethical questions. Does the cosmos have moral standing independent of its usefulness to humans? Do we have obligations to preserve pristine star systems, or is it acceptable to exploit them for resources and colonization? Terrestrial environmental ethics has evolved from pure anthropocentrism, where nature matters only as it benefits humans, toward recognition that ecosystems, and perhaps even individual organisms, have intrinsic value deserving moral consideration. As we contemplate expanding into space, should we extend this ethical expansion cosmically? The Outer Space Treaty of 1967 includes provisions against harmful contamination of celestial bodies and requires that space exploration be conducted for the benefit of all countries. But these provisions were written with solar system exploration in mind, not galactic colonization. They provide limited guidance for interstellar ethics. Some argue for a preservationist approach. We should minimize our impact on cosmic environments, preserving pristine star systems and only developing systems that lack scientific value or potential for indigenous life. This perspective values the cosmos as it naturally exists, seeing human expansion as potentially destructive of something irreplaceable. Others argue for a developmentalist approach. The cosmos is vast and mostly empty. Stellar systems will eventually be destroyed when their stars die anyway, and human civilization is itself valuable and worthy of expansion. From this perspective, transforming dead matter into living, conscious civilization increases rather than decreases the universe's value. A middle position might hold that we should expand but carefully, preserving systems with unique scientific value, searching thoroughly for any signs of life before developing systems, minimizing unnecessary destruction, and maintaining some fraction of the galaxy in its natural state for study and aesthetic appreciation. The discovery of any form of extraterrestrial life, even microbial, would intensify these ethical debates. Does bacteria on a distant moon have rights? Should we refrain from colonizing systems with any life, even if that life is simple and the system otherwise perfectly suited for human use? What if useful resources exist only in systems with life? These questions have no obvious answers. Different philosophical and religious traditions would provide different guidance. Some might hold that all life is sacred and must be preserved. Others might argue that only complex life deserves moral status. Still others might propose that human consciousness and civilization represent the highest value, justifying development even at the cost of simpler life forms. The environmental impact of the highway infrastructure itself warrants consideration. Navigation beacons, communication relays, and waypoints would scatter artificial objects throughout interstellar space. While the cosmos is vast and these objects tiny by comparison, they represent a permanent human presence, altering the pristine environment. More significantly, propulsion systems might have environmental consequences. Nuclear pulse propulsion releases radioactive materials. Antimatter annihilation produces intense radiation. Laser propulsion requires enormous energy generation, potentially drawing significant fractions of stellar output. These activities could theoretically affect local space environments, though likely negligibly given the vast scale of space. A potentially more serious concern is the risk of spreading Earth life throughout the galaxy, either intentionally through terraforming or accidentally through contamination. Earth organisms hitchhiking on spacecraft could potentially colonize alien worlds, outcompeting or destroying any indigenous life. This could constitute an ecological catastrophe on a cosmic scale, effectively committing genocide against alien biospheres through negligence. Preventing such contamination would require rigorous sterilization protocols, careful control of biological materials, and possibly restrictions on what can be carried on interstellar voyages. But perfect sterilization may be impossible, and economic pressures might encourage shortcuts. The history of invasive species on Earth suggests that biological contamination is difficult to prevent once travel becomes routine. Perhaps most profound are the questions about what interconnectedness means in a universe with light speed limits. On Earth, we increasingly conceive of humanity as a single interconnected global civilization. The internet, international trade, rapid travel, and instant communication create genuine real-time connections across the planet. Events in one location affect others almost immediately. An interstellar highway would create a very different kind of interconnectedness. Colonies would be connected but not in real time. They would share information, trade goods, acknowledge common origins, and maintain relationships, but would experience their daily lives essentially independently. This is interconnectedness without simultaneity. relationship without real-time interaction. This challenges our notions of community and civilization. Can communities separated by decades of communication delay truly be one civilization? Or are they necessarily separate, merely maintaining historical connections like ancient Greek colonies maintained connections to their mother cities while functioning independently? Perhaps we need new conceptual frameworks for thinking about relationship and community across such scales. A galactic civilization would not be a single entity but a network, a web of relationships spanning space and time, with each node operating autonomously while remaining part of a larger whole. This has implications for identity and belonging. A person born on a colony 50 light-years from Earth might never communicate with Earth in real time, might never meet anyone from Earth, and might live in a culture radically different from Earth's. Yet they would know their ancestors came from Earth, would have access to Earth's history and culture through the information archive, and might feel kinship with Earth despite the vast distance. Would such a person consider themselves human, Earthling? Or would they identify primarily with their local colony and its unique culture? Identity would likely be layered, local identification strongest, with broader human identity as a more abstract layer acknowledging shared origins without implying current unity. The highway itself might become a source of identity and meaning. Those who work on or travel the highway, those who maintain the infrastructure or staff the waypoints, might develop an identity as highway people, cosmopolitan wanderers who belong everywhere and nowhere, whose community is the network itself rather than any particular location. This lifestyle would be analogous to historical merchant sailors, who spent most of their lives at sea, visiting many ports but belonging to none, forming communities aboard ships rather than on land. The interstellar highway might create a new category of people whose identity is defined by movement and connection rather than by place. The philosophical implications extend to questions of meaning and purpose. Why should humanity build an interstellar highway? What is the point of spreading across the galaxy? Various answers might be offered. Some are practical: survival through distribution, access to resources, continuation of growth and development. Others are more philosophical: fulfilling humanity's destiny as explorers, increasing consciousness and complexity in the universe, creating beauty and meaning on a cosmic scale. Some might argue that expansion is simply what life does, what consciousness does. Life has spread across Earth into every available niche. Intelligence seeks to understand and transform its environment. Building an interstellar highway might be the natural continuation of this pattern, not requiring justification beyond its own nature. Others might argue that we should justify such an enormous undertaking, ensure it serves genuine human values and doesn't merely satisfy restless ambition. Perhaps we should perfect our civilization on Earth before spreading to the stars, avoiding the export of our problems and conflicts to a galactic scale. This debate mirrors historical arguments about exploration and colonization. Some have always championed expansion as progress and destiny. Others have questioned whether expansion serves humanity's deepest needs or merely distracts from unresolved problems. There is no objectively correct answer. Different people with different values will reach different conclusions. What seems clear is that building an interstellar highway would be a commitment to a particular vision of humanity's future: outward-looking, expansionist, technological, and ambitious. It would represent a choice that humanity as a whole has meaning and purpose beyond survival on a single world, that we should strive to become something more than we are, even if that transformation takes thousands or millions of years. This choice has ethical weight. It would affect countless future generations, committing them to lives as spacefaring people, whether they would choose this path or not. It would alter the galaxy, potentially affecting other life forms we have not yet discovered. It would transform human nature itself through adaptation to diverse environments and divergent evolution. Are we wise enough to make such choices? Do we have the right to make them on behalf of future generations and potential alien life? Or is inaction also a choice? One that condemns humanity to remain on Earth and eventually perish when our sun dies or earlier catastrophe strikes? Perhaps the most honest answer is uncertainty. We cannot know the full consequences of building an interstellar highway. We cannot foresee how it will change us or what we will become. We cannot predict what we will encounter among the stars. We can only make our best judgment with limited knowledge and imperfect wisdom, hoping that the values guiding us, compassion and curiosity, and the drive to flourish and create, are sufficient foundation for decisions whose effects will ripple across light years and millennia. The interstellar highway, if built, would be among humanity's most consequential creations, comparable to the development of language, agriculture, or civilization itself. It would not merely be infrastructure, but a philosophical statement that humanity chooses to expand, to explore, to connect, to become more than we are. It would embody both our noblest aspirations and our concerning tendencies, both our wisdom and our hubris. Whether this grand project represents humanity's finest achievement or greatest folly might not be clear for thousands of years, long after the decisions have been made and the consequences set in motion. Future historians, human or otherwise, will judge whether we chose wisely. All we can do in the present is think carefully, debate thoroughly, consider ethics alongside engineering, and proceed with both ambition and humility, reaching for the stars while remaining mindful of our responsibility to do so thoughtfully and well. The roads we build between the stars will carry not just ships and goods, but the hopes and values of our civilization. They will be pathways into the future, and what future we reach depends on the wisdom we bring to their construction. The interstellar highway would be, in the end, not just a physical network, but a moral and philosophical statement about who we are and who we choose to become. That choice, perhaps, is the most profound question of all. In 1903, the Wright brothers achieved sustained, controlled, powered flight for the first time in human history. Their aircraft, the Wright Flyer, traveled 120 feet in 12 seconds, barely skimming above the ground at Kitty Hawk, North Carolina. The achievement was remarkable but modest. The machine was fragile, difficult to control, and impractical for any purpose beyond demonstration. Skeptics abounded. Many serious scientists and engineers had declared heavier-than-air flight impossible. Even after the Wright brothers' success, critics dismissed aviation as a curiosity with no practical future. The US Army initially rejected the technology. Newspapers barely covered the story. The idea that within a century, millions of people would routinely fly across oceans in vehicles traveling hundreds of miles per hour would have seemed absurd fantasy. Yet 66 years after that first 12-second flight, humans walked on the moon. The impossible became routine within a single human lifetime. Technology that existed only in imagination became reality through incremental progress, unexpected breakthroughs, massive investment, and the accumulated work of millions of people. Today, we stand at a similar threshold regarding interstellar travel. The distances are vastly greater, the challenges far more daunting, the timescales much longer. Yet the journey from our current capabilities to a functioning interstellar highway system, while extraordinarily difficult, may not be impossible. Understanding where we are now, what breakthroughs are needed, and what path might lead forward can help us assess whether this vision is achievable reality or permanent fantasy. Our current position is, to be blunt, extremely primitive. We have sent exactly 12 humans beyond low Earth orbit, all to the moon, the last in 1972, more than 50 years ago. Our robotic probes have explored the solar system extensively, but only 5 spacecraft have achieved enough velocity to eventually leave the solar system entirely. Pioneer 10 and 11, Voyager 1 and 2 and New Horizons. Voyager 1, launched in 1977 and currently our most distant artifact, travels at about 17 kilometers per second relative to the Sun. At this velocity, it would require roughly 75,000 years to reach Proxima Centauri if it were headed in that direction, which it is not. This is our fastest achieved velocity with current technology, and it is nowhere near adequate for practical interstellar travel. The Voyager probes were not designed for interstellar travel, but for exploring the outer solar system. They achieved their velocity through gravitational assists from Jupiter and Saturn, essentially borrowing momentum from these giant planets. This technique works within our solar system, but cannot be extended to interstellar distances in any straightforward way. Our propulsion technology remains fundamentally limited. Chemical rockets which powered the Apollo missions and most current spacecraft have reached their theoretical performance limits. Ion drives, which use electric fields to accelerate ions to high velocity, provide better efficiency but very low thrust, making them suitable only for missions where gradual acceleration over months or years is acceptable. Nuclear propulsion exists only in theoretical designs and limited testing. Project Orion, which studied nuclear pulse propulsion in the 1950s and 60s, produced detailed designs but was never built due to the Partial Test Ban Treaty and concerns about nuclear weapons proliferation. Nuclear thermal propulsion, where a reactor heats propellant, has been tested in prototype but never used operationally. Fusion propulsion, antimatter propulsion, and more exotic concepts remain entirely theoretical. We have not yet achieved net positive fusion energy, even in stationary laboratory conditions, let alone in a compact propulsion system. Antimatter production remains limited to nanograms per year at enormous cost. These technologies are not on the cusp of deployment, but remain decades away at minimum, possibly much longer. So where are we truly in terms of making the first step toward an interstellar highway? The honest answer is that we are in the very earliest conceptual stage, analogous to the state of aviation in the late 1800s, when people were still figuring out whether heavier-than-air flight was possible. However, important groundwork is being laid. The Breakthrough Starshot initiative, announced in 2016, aims to develop the technology to send gram-scale probes to Alpha Centauri at 20% of light speed using laser propulsion. The project is a serious scientific endeavor, though it faces immense technical challenges and may take decades to achieve its goals if it succeeds at all. NASA and other space agencies continue to study advanced propulsion concepts. The NASA Innovative Advanced Concepts Program funds early-stage research into technologies like fusion propulsion, antimatter storage, and electromagnetic sails. These are small-scale research efforts, not major development programs, but they keep the knowledge and expertise developing. Private spaceflight companies like SpaceX, Blue Origin, and others are dramatically reducing the cost of reaching Earth orbit, which is a necessary first step for any interstellar ambitions. The development of reusable rockets has reduced launch costs by an order of magnitude, and further reductions may be possible. Cheap access to space enables infrastructure development in our solar system, which could eventually support interstellar missions. More fundamentally, our scientific understanding of physics continues to advance. We are exploring the boundaries of known physics through experiments at particle accelerators, gravitational wave observatories, and astronomical observations. While we have discovered no loopholes allowing faster-than-light travel, we continue to refine our understanding of fundamental forces and the structure of space-time. For a true interstellar highway to become reality, several major breakthroughs would need to occur across physics and engineering. First, propulsion technology must advance dramatically. At minimum, we need fusion propulsion capable of achieving 10 to 20% of light speed with reasonable mass ratios. This requires solving the fusion energy problem that has eluded us for decades, then miniaturizing the technology enough to fit on a spacecraft while maintaining favorable power-to-weight ratios. Alternatively or additionally, we might develop practical antimatter production and storage. This requires finding ways to produce antimatter far more efficiently than current methods allow, possibly by harvesting it from natural sources rather than producing it in particle accelerators. It also requires developing ultra-reliable magnetic containment, systems that can safely store significant quantities of antimatter for years or decades. Laser sail technology needs to advance to the point where it can accelerate not just gram-scale probes but larger payloads, possibly through stage systems where each stage provides incremental boosts. The laser arrays would need to scale from the 100 gigawatt systems proposed for Breakthrough Starshot to potentially terawatt-scale systems for larger missions. Second, we need dramatic advances in life support and suspended animation. Humans cannot realistically remain conscious and active for multi-decade journeys with current technology. The resource requirements, psychological strain, and radiation exposure make this untenable. We need either reliable suspended animation, allowing crew to sleep through most of the journey, or generation ship technology, creating self-sustaining ecosystems that support multiple generations. Suspended animation, sometimes called cryogenic sleep or hibernation, remains entirely theoretical for humans. We can freeze and revive some organisms, and we can induce hibernation-like states in some mammals. But reliably suspending and reviving humans without damage is beyond current capability. Significant advances in understanding metabolism, cellular preservation, and revival processes would be needed. Generation ship technology requires closed-loop life support systems far more reliable than anything currently existing. The International Space Station requires regular resupply from Earth. A generation ship must recycle air, water, and waste with near-perfect efficiency for decades or centuries, producing food through agriculture or other means, and maintaining habitability across multiple human generations without resupply. Third, we need revolutions in artificial intelligence. As discussed in earlier sections, an interstellar highway absolutely requires sophisticated AI capable of autonomous operation over decades. This means not just narrow AI that performs specific tasks well, but general AI with flexible problem-solving ability, long-term planning capacity, and the ability to handle novel situations without human guidance. Current AI excels at specific tasks: image recognition, language processing, game playing. But AI systems remain brittle, struggling when confronted with situations outside their training distribution. For interstellar applications, we need robust AI that can operate reliably in unpredictable environments, diagnose and repair unfamiliar problems, and maintain safe operation across timescales far exceeding current AI deployment scenarios. This also requires solving AI safety and alignment problems. An AI system deployed on an interstellar mission will operate beyond human oversight for decades. We must be confident it will pursue its intended goals, handle ethical dilemmas appropriately, and not develop harmful behaviors. This is an active area of AI research, but remains unsolved. Fourth, materials science must advance substantially. Interstellar spacecraft need materials that can withstand decades of radiation exposure without degrading, maintain structural integrity under extreme temperatures and stresses, provide effective radiation shielding at reasonable mass, and possibly self-repair or adapt to damage. Metamaterials with engineered properties, carbon nanotubes and graphene-based structures, advanced ceramics, and perhaps materials designed at the atomic level using nanotechnology could provide the necessary performance. But these remain largely laboratory curiosities rather than proven technologies for large-scale space structures. Fifth, we need breakthroughs in power generation and energy storage. Interstellar spacecraft and infrastructure need compact, long-lived power sources, radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity, power current deep space probes, but they provide only modest power levels and gradually decline in output as their radioactive fuel decays. For larger missions, we likely need compact fusion reactors, providing megawatts or gigawatts of continuous power from minimal fuel mass. Alternatively, advanced solar cells combined with laser power beaming might provide energy to ships and infrastructure, though this works only within a few light months of stars or laser stations. Beyond these engineering challenges, certain physics questions remain open. Most fundamentally, is faster than light travel possible through any mechanism? Our current understanding says no, but physics has surprised us before. Warp drives and wormholes remain theoretical possibilities, consistent with general relativity if exotic matter with negative energy density exists, which has never been observed. If negative energy matter proves impossible, as many physicists suspect, then faster than light travel is likely permanently impossible, and interstellar travel will always be constrained by light speed limits, making journeys take decades or centuries. If negative energy matter exists and can be produced or found, it would revolutionize interstellar travel more than any other single development. Other physics questions matter as well. Are there undiscovered propulsion principles we might exploit? Does the quantum vacuum contain extractable energy, as some speculative theories suggest? Are there shortcuts through higher dimensional space? These questions remain open, with most physicists skeptical but not completely dismissive. Given these challenges, could an interstellar highway become reality in the next few centuries? Or does it remain pure science fiction? The answer depends on which breakthroughs occur and how quickly. A pessimistic scenario. Fusion power proves more difficult than expected, taking another century to achieve practical energy generation and longer still to miniaturize for propulsion. Antimatter production remains impractically expensive. AI progress plateaus before achieving the autonomy needed for interstellar missions. Materials and life support technology advance only incrementally. In this scenario, interstellar travel remains impossible or impractical throughout the 21st and 22nd centuries. The first crewed missions to another star might not launch until the 23rd or 24th century, arriving in the 25th century or later. A true highway network would be many centuries beyond that. A moderate scenario. Fusion propulsion becomes practical by the late 21st century. AI continues advancing, achieving the necessary autonomy by mid-22nd century. Materials science and life support technology progress steadily. Laser sail technology successfully sends probes to nearby stars in the late 21st century, followed by larger missions in the early 22nd century. The first crewed missions launch in the mid-22nd century, perhaps arriving at Alpha Centauri around 2200. Basic highway infrastructure, navigation beacons and communication relays begins deployment in the early 23rd century. A rudimentary network connecting the nearest handful of stars exists by the mid-23rd century, maturing over the following centuries. An optimistic scenario. Multiple breakthroughs occur more rapidly than expected. Fusion propulsion is achieved by mid-21st century. Unexpected discoveries, perhaps in materials science or physics, dramatically improve propulsion efficiency. AI advances rapidly, possibly achieving artificial general intelligence by 2050. Suspended animation becomes practical. Massive investment, driven by resource concerns or existential risk awareness, accelerates development. Probe missions reach nearby stars by 2070 or 2080. Crewed missions follow by the early 22nd century. Infrastructure deployment begins immediately, with basic highway network connecting several nearby stars by 2150 to 2200. Which scenario is most likely? History suggests that radical technologies often take longer than optimists predict, but less time than pessimists believe. Aviation took roughly 50 years from first flight to becoming routine passenger transport. Nuclear power took about 20 years from first controlled reaction to commercial power plants. The internet took about 30 years from initial protocols to widespread adoption. Interstellar travel is far more difficult than these technologies, but it is not necessarily impossible. A realistic estimate might place the first serious interstellar missions in the late 21st or early to mid-22nd century, with a basic highway network developing over the following 2 to 3 centuries. This is within the realm of possible within a handful of centuries, rather than pure science fiction or imminent. Scientists and futurists have indeed imagined what the first galactic road network might look like, and their visions share certain common features despite varying details. Most envision a hub-and-spoke structure initially, with Earth and our solar system as the hub and routes extending like spokes to the nearest stars. Alpha Centauri, Barnard's Star, Wolf 359, and others within 10 light-years. These initial routes would be bare bones, basic navigation beacons, limited communication relays, perhaps a few waypoints along each route. The initial missions would be exploratory and experimental, establishing proof of concept that interstellar travel and infrastructure deployment are feasible. Each mission would refine techniques, test technologies, and gather data informing subsequent missions. The learning curve would be steep, with early missions likely suffering high failure rates. As routes mature, infrastructure would gradually expand. More beacons and relays would fill in gaps, increasing reliability and coverage. Waypoints would grow from simple automated stations to more sophisticated facilities with repair capabilities and eventually human presence. The routes would become progressively safer and more efficient through experience. The network would then begin expanding beyond the initial hub-and-spoke pattern. Once colonies are established at nearby stars, they would launch their own missions to stars near them, creating a second generation of routes not centered on Earth. This would gradually build a web or network structure, with multiple interconnected routes allowing travel between many star systems without necessarily routing through Earth. Some futurists imagine the network developing distinct regions or corridors. The inner sphere, perhaps encompassing stars within 20 or 30 light-years of Earth, would be densely connected with frequent traffic and extensive infrastructure. Beyond this would be a frontier zone with sparser infrastructure and fewer routes, gradually expanding outward. Beyond the frontier would be unexplored space, the target of reconnaissance missions seeking new systems to add to the network. Others imagine the network developing along natural corridors defined by stellar distribution. Stars are not uniformly distributed but tend to cluster in certain regions while other regions are sparse. The highway might naturally follow regions of higher stellar density, where shorter distances between stars make route establishment easier, while leaving voids with few stars relatively unexplored. The science fiction author and physicist Robert Forward proposed highly detailed concepts for interstellar missions using technologies like laser sails and antimatter propulsion. His designs, while speculative, are grounded in physics and provide concrete examples of what early interstellar infrastructure might involve. Other scientists have proposed similar detailed concepts, creating a body of serious technical literature on interstellar mission design. The physicist Freeman Dyson, among others, has discussed the long-term possibility of Dyson spheres or swarms, megastructures capturing significant fractions of a star's energy output. While such structures are far beyond current capability, they represent the scale of infrastructure that might eventually support advanced interstellar civilization. A mature highway system might be supported by such massive infrastructure, using stellar-scale energy capture to power laser arrays, antimatter production, or other high-energy applications. The astronomer Frank Drake and others involved in SETI have considered what an interstellar civilization's communication network might look like. Their work on detecting potential alien signals informs thinking about how humanity's own interstellar communication network might function, what frequencies to use, what protocols to employ, and how to maximize range and reliability. Some futurists imagine that the first galactic road network might not be built by humans alone, or even primarily by humans. If we develop sufficiently advanced AI before achieving interstellar travel, we might send AI explorers and constructors first, with humans following later once the AI has established infrastructure. This could dramatically accelerate network development, as AI need not be kept alive during long journeys and can work tirelessly for centuries without the limitations of human biology. This raises interesting questions about whether the network would be fundamentally human infrastructure or something else, managed and perhaps even designed by AI for eventual human use. The distinction between human and AI agency may blur in ways that make such questions ultimately meaningless, but they reflect genuine uncertainty about how interstellar expansion would proceed. The timescales involved mean that any interstellar highway network would be built not by a single generation, but by many successive generations, each contributing incrementally to a project whose completion they will never see. This requires a kind of long-term thinking and intergenerational commitment that human societies sometimes achieve. Cathedral builders in medieval Europe, the planners of the Great Wall of China, or the Polynesian navigators who gradually settled the Pacific over many generations. Whether modern civilization, with its short-term focus and rapid cultural change, can sustain such long-term projects is an open question. Perhaps the very act of committing to interstellar expansion would transform our cultural relationship with time, forcing us to think in terms of centuries and millennia rather than quarters and election cycles. The first step toward an interstellar highway, in practical terms, might not be a spacecraft launch, but a commitment, a decision by humanity, or a significant portion of it, to seriously pursue interstellar travel as a long-term goal. This would mean sustained investment in necessary technologies, training generations of scientists and engineers, building the industrial and economic infrastructure to support eventual missions, and maintaining focus across decades, despite competing priorities and inevitable setbacks. Such commitment requires vision and leadership. Someone must articulate why interstellar travel matters, what it offers humanity, why it is worth the enormous investment of resources and talent. This is as much a philosophical and political challenge as a technical one. The speeches and writings that inspire commitment to an interstellar future have not yet been fully written. The political consensus has not yet formed. The cultural shift toward thinking of humanity as necessarily multi-star has not yet occurred. Yet, there are encouraging signs. The growing awareness of existential risks creates motivation to ensure humanity's survival beyond Earth. The increasing plausibility of discovering life on exoplanets generates public interest in other star systems. Private space ventures demonstrate that spaceflight need not depend solely on government funding. The accelerating pace of technological change, while sometimes frightening, also creates a sense that previously impossible achievements may be within reach. We stand today perhaps where aviation stood in the 1890s. The basic physics is understood. Serious people are working on the technical challenges, but practical implementation remains just beyond the horizon. The first tentative flights, equivalent to the Wright brothers' 12 seconds at Kitty Hawk, might occur within decades. Laser sail probes reaching nearby stars, perhaps, or breakthrough advances in fusion propulsion technology. From those first small steps to a true interstellar highway would require further decades or centuries of development, analogous to the progression from the Wright Flyer to modern aviation. But if history is any guide, once the basic capability is demonstrated, progress can accelerate rapidly when economic and social forces align to drive development. The interstellar highway remains, for now, more aspiration than reality, more blueprint than building. But blueprints can be built from aspirations can be achieved. The first roads were once just paths that people walked repeatedly until their passage wore a visible trail. The interstellar highway might begin similarly, a few probes, then a few ships, following paths that others will eventually widen into routes, then corridors, then highways carrying civilization to the stars. Whether this future arrives in 200 years or 2000, whether it comes through steady incremental progress or unexpected breakthrough, whether humans build it or humans and AI together, the path forward exists. The laws of physics do not forbid it. The technologies, while difficult, appear ultimately achievable. The motivation, survival and curiosity, and the human drive to expand and explore certainly exists. The interstellar highway awaits not discovery, but decision. The decision to commit, to invest, to work across generations toward a goal that transcends any individual lifetime. That decision has not yet been fully made, but it could be. And if it is, the age of interstellar civilization, with its highways connecting the stars, would not be science fiction, but an eventual reality. The next chapter in humanity's story, written across light years and centuries, in infrastructure and achievement that would make even the greatest works of our past seem provincial by comparison. The future beckons. The road to the stars lies before us, waiting to be built.